Hi, and welcome to the course on forecasting models in Excel. It is important for marketing analysts and managers to accurately forecast future sales. Sales forecasts drive decisions involving manpower planning, production scheduling, inventory management, etc. In this course, we will explore how we can use analytics to forecast future sales and revenue. Let me give you a brief overview of this course. You will first learn the regression modeling technique using which we establish the relationship between different predictor variables and the variable whose value we want to predict. Once we know the relationship, we can predict the values for any new set of predictor variables. Then you learn how to estimate the trend and seasonal aspects of sales and generate forecast including these effects. We also learn how to include the effects of special events such as holiday sales, match nights, etc. Then we learn two common extrapolation forecasting methods like moving average method and Winters method. Winters method is an exponential smoothing method which includes trend and seasonality effects. In the last section, we also cover techniques to forecast new product sales. It is difficult to forecast when we have little or no historical data. The S curve can be used when we have little data, and the famous Bayes diffusion model can be used to predict product sales even before the product is launched in the market. All these forecasting models are actually used by marketing analysts and consulting firms to forecast future product sales and revenue. Since we are going to create all these models in Microsoft Excel and it will be pretty advanced level of Excel, we have included some basic video lectures on how to use Microsoft Excel also. In the course, we will understand the concept and analytics behind different forecasting models and develop an intuition that which model works where. The concepts would be taught using a presentation such as this one. Corresponding to each theory lecture, there will be a practical class in which we will learn how to build that particular model in MS Excel. These practical classes are going to be very interesting and will definitely be something that you won't find in any other online course. You can see that the course curriculum is pretty comprehensive with topics ranging from basic to some really advanced ones. Be assured that at the end of this course, you will be feeling confident in logically building your own custom forecasting model for your business scenario. So if you're ready to learn, we are happy to have you and see you in the next video. As marketing managers, you will often face questions like, how will demand for my product change if I change the price? How will my sales be impacted if I increase or decrease advertising budget? What is the importance of product placement in the store on the number of units sold? When marketing managers face such questions, what they actually want is to establish the relationship between variables. In this section, we are going to learn some simple tools such as linear regression, which can help us model this relationship. In this lecture, I am going to define some important terminologies which will be used throughout the course. First is a dependent or response variable. This is the variable for which we want to predict the value. Then we have independent or predictor variables. These will be the variables which we are going to use for prediction purposes. For example, if you wanted to answer the question that how will your sales change if you increase online marketing and decrease offline marketing, the dependent or the response variable would be the sales amount. This is the value that you want to predict how it is changing. And the independent or the predictor variables is going to be the amount of spend you are going to do in online or offline marketing. So spend in online and offline marketing will be your independent variables and net sales would be your dependent variable. This statistical technique that we are going to use to model this relationship is linear regression. In linear regression, we assume a linear relationship between independent and dependent variables. By linear relationship, I mean that the dependent variable, which is represented by y in this equation, is linearly related with all the independent variables which are represented by x1, x2 up to xn. By linear relationship, we mean that if I increase the value of x1 by 1 unit, y will increase by a1 units. Similarly, if we increase the value of x2, y will increase by a2 units and so on. So in our example of how sales will be impacted by changing the online and offline marketing spend, our y would be the total sales, x1 would be the online marketing spend, x2 would be the offline marketing spend, and we would try to find out the value of a0, a1 and a2 to establish the relationship between total sales and online and offline marketing spend. Once we have the value of a0, a1 and a2, we can put any new value of x1 and x2, that is online and offline marketing spend, to predict the total sales in the future. Apart from this, in the next 5 videos, we'll be teaching basics of statistics. So if you know terms like mean, median, mode, categorical or qualitative variables, etc., you can skip the next 5 lectures. Else, I recommend that you understand the terms taught in the next 5 lectures before moving on. After the basics, we will learn some very important concepts of data collection, data cleaning and data pre-processing to get the data ready for analysis. This section is very important and almost no book or course tells you how to do this, whereas this is one of the most important steps of building a forecasting model. Once the data is ready to process, we will run simple linear regression and multiple linear regression on it, and we will understand how to interpret the results. In this section, we are going to use one data set, which will be the house pricing data set. Using that data set, we are trying to achieve two outcomes. First outcome is we want to be able to predict house prices given the value of other variables. And the second outcome is we want to identify the impact of different variables on the house price. That is, we want to establish which all variable is important and changing which variable by how much amount will change house price by how much amount. The steps that you will learn in creating this model are generalized steps. You can use any data set, clean it and pre-process it as told in the coming videos, and use that data set to predict your dependent or response variable using the other independent variables. These steps remain the same. You can change the data set according to your marketing problem.
First of all, I want to congratulate you for starting this course. You may not know this, but out of all the enrolled students, only 20% reach this point. So you are already in the top 20% of the students. We hope that you continue the same energy and motivation throughout the course and complete this course. Students like you inspire us to create a 5-star course by motivating us to continuously upgrade the course, add additional resources, and answer your queries. I also want to give you some information about the Udemy course review system. Udemy may ask you to provide course rating after a couple of lectures. So do rate our teaching quality. If you feel that you have not gone through enough lessons, you can skip this for now and rate the course at a later point using this edit your rating option. If you face any technical issues like video blurring or audio muting, you can change the video player setting from here. If the problem persists, you can contact the technical support of Udemy. All of our lectures have gone through the extensive quality check of Udemy, and I assure you that there is no technical problem with any of our lectures. Also, you may not be satisfied with the pace of this course. You may find that the course is either too slow or too fast. To adjust this, you can change the pace from this playback rate button in the Udemy video player. Also, you may have noticed that I have a very strong Indian accent in my voice, but I'm trying to make it as neutral as possible. You can also enable English subtitles using this button to help you through this course. Apart from this, if you have any course related queries or suggestions, you can reach out to us through direct messages or Q&A portal. For direct message, go to our StarTech Academy profile and click on the send message button. For Q&A, just go to the Q&A tab and ask your question. Pukhraj and I will personally solve all your doubts and questions. Again, rate us on our teaching skills and contents. It would be better if you can write a review along with the star rating. It will help us in promoting the course, and it will also help other people to take the decision on which course to buy. Once again, congratulations. You are already among the top 20% students of this course. Keep up the good work and complete this course. Remember what Mahatma Gandhi told us about learning. Live as if you were to die tomorrow, and learn as if you were to live forever.
In this video, we are going to see a very simple technique using which you can estimate the relationship between two variables, that is only one independent and only one dependent variable. This can be done by using the scatter plot option in Microsoft Excel. So let us see how to do that. Here is the complete data set which has price, which was our dependent variable, and all the other independent variables. Now, if I want to predict the value of price using only one variable, say I want to see the relationship between room num, that is number of rooms, and the price of the house. To do that, I will take out these two columns and paste it in a separate sheet. You can select the complete column by selecting the first cell and then pressing Ctrl plus Shift plus down key on your keyboard. Then you can paste it in the destination cell by just pressing Ctrl V. Now we have the room num variable, which is our independent variable, using which we want to predict the value of price. That is, we want to find out the relationship between number of rooms in the house and the price of that house. So to do that, we will first plot these values on a scatter plot. We select all the values, we go to Insert, and we select this scatter plot option. The scatter plot is plotting each point on this x and y axis graph. The number of rooms, that is room num variable, is on the x axis. The price is on the y axis. So the first point, which is 6.5, 24, is nearly at this location. Similarly, each point from the data set is plotted on this graph. Now using this graph, you can visually identify that there is some linear kind of relationship between these two variables. That is, as the number of rooms are increasing, the price of house is also increasing. Now, as I told you earlier, we are trying to estimate a linear relationship between these two variables. That linear relationship is graphically represented by a straight line. So the straight line giving the relationship between these two variables can be added by clicking on this plus symbol, going to the trend line option, and here selecting the linear option. You can see a dotted blue line, which is a straight line, giving us the trend of relationship between price and room num. Although a lot of points do not exactly fall on this trend line, but this is the line which is as close to all the points as possible. In the later videos of this course, you will understand why is this line the best fit by understanding the mathematics behind estimating this line. For now, this is how we get the best fit straight line between two variables. Now, if you want to look at the equation of this line, we need to right click on this line and go to format trend line option. You can see that we have formatting options on the right. Here linear is pre-selected since we plotted a linear trend line. If we scroll down, you can see the two checkboxes. One checkbox is saying display equation on chart. If you tick this, you can see the linear equation representing the relationship between price and room num. Here y is for the price variable since it is on the y-axis, and x is for number of rooms. If you look at this equation, you can see that if I increase the number of rooms in the house by 1 unit, the value of y will increase by 9 units because x is multiplied by 9.09. So using that equation, whenever we have the number of rooms available with us, we can predict the price of the house. For example, if I want to predict the price of house which has 8 number of rooms, we can do that by writing 9.099 multiplied by this cell which contains the number of rooms minus 34.66. So the house of price with 8 number of rooms is 38.13 units. You can just change the number of rooms here to get the updated price. So if I have 10 rooms, it is 56.33 units. Now there is a quantity called R-square which gives us how well is my line predicting the relationship between the two variables. We will understand the concept behind R-square in the later videos, but for now, if you want to look at the value of R-square, you can just select the trend line, go to its formatting options and tick this last checkbox. You can see that the R-square value is coming out to be 0.48. The R-square values remain between 0 and 1, where 1 means that it is a excellent fit and 0 means that it is a very poor fit. Our R-square value is coming out to be 0.5, which is average, and we will discuss in detail what is a good R-square value in the later videos. So the method that we discussed in this video of using only two variables, plotting a scatter plot and then plotting a trend line and seeing its equation is the simplest way you can find a relationship between two variables using Microsoft Excel. However, it has limitations since you can use only two variables, plus it has limitations in terms of type of data that you are using. Moreover, for the data set that we have a lot of independent variables and we want to use all of them to predict the value of price. In such scenarios, this method will not work. Therefore, we will learn how to create a step-by-step linear regression model which will overcome all these limitations. So let's start with the first thing you should know when you are trying to solve a problem. You should know about the business context of that problem. You should know what all factors are important and have impact on the variables of interest. Only if we know the business, we will be able to identify relevant variables and gather required data for the analysis. Remember this, the quality of your inputs will decide quality of your outputs. Now there are two primary ways to gather information about business. One is to gather it yourself by talking to relevant people or stakeholders of that business, people who are impacted by the problem at hand. Or you can also gather information by actually doing the things yourself. For example, if you have to increase sales of a particular product, try to go and sell it yourself in the market. Go and try to buy it also to understand customers' perspective. Gathering information by yourself is called doing primary research. In secondary research, you read or listen to the information gathered by others. Maybe there is some industry related research report or some study done by some consulting firm or someone else has worked on this same problem before. We should look at methodology and findings of those earlier works also. Here is an example. Suppose you are part of a company which sells online and the problem you are facing is of cart abandonment. That is, a lot of your customers add product to their cart but do not actually purchase it. This is a fairly common problem for online businesses. Now, if you are given the task to tackle this problem, where do you start? First, we should go and talk with the relevant teams involved. Usually, there is a marketing team and a product team which cross-functionally handle the online sales process. We should go and talk to them. Then, we should try purchasing from the site ourselves also to understand what is the customer journey online. All this will be primary research. As part of secondary research, we should look for previous studies on cart abandonment within and outside the organization. Once we have done all this, we would have fairly good idea of what all variables and what type of model we are going to use. Next task is to get the data. Once we have business knowledge, we need to gather the relevant data. There are 3 steps to it. First is to identify the data needed. We know what data we need from the research. Second is requesting this data from relevant people within and outside the organization. And lastly, when you receive the data from different teams, you need to do a quality check on the data received. Data being requested can be of 2 types, internal data and external data. Internal data is the data which is collected by you or your research team or your organization. For example, sales data or monthly money spent on a particular type of promotion is the data available with your organization and is internal data. External data is data collected and maintained by external data sources. For example, governments maintain a population census data which can be used to determine the demography in a particular region, or you can buy data from several third-party vendors also. Now let's go back to the example of cart abandonment. We decided to go meet some people and do some secondary research. Let us see how business knowledge tells us what data to gather. So first we went to the marketing team. They tell us that customers who are coming to the website are coming from three different channels. 50% come from email marketing, 30% from organic search, and 20% from AdWord marketing. Probably whether the customer will eventually buy or not buy depends on which channel that customer is coming from. So we decide to get the source data to our website for all the customers. Next, product team tells us that there are 3 steps in the buying process after adding a product to cart. Cart review, adding address or personal details, and then finally the payment. Maybe there is some issue in any particular step. Let's gather the cart abandonment location for all the customers. Then we read some industry reports regarding the issue and found out the below observation. Customers who add expensive items in their cart keep it in the cart for longer duration. So against each customer order, we should also get the total cart value for each customer. Lastly, when we did our dry run, we saw that there is a small survey link to rate the experience. So let's get these ratings from the customer experience team also. You can see how business understanding is telling us what data to collect. Once you have the data, you need to tidy it up and clearly define what each variable stands for. So here is the data that we are going to use in this course. The problem statement here is that you are a manager in a real estate company and you want to find out the true value of a property. That is, basis the pricing of past property transactions, you want to get the price of the property you want to sell. So, price of a property will be the dependent variable in our analysis, and other factors which impact the price, which we identified basis primary and secondary research, are the independent variables. This dataset has values for all these variables. Whenever we collect data, different parts of data come from different sources, and you need to collate this data into a single tabular format such as this. In this table, the header row tells us the variable names. While keeping variable names, try not to use space. Instead, use an underscore. For example, in crime rate, we have used crime underscore rate. This is because some softwares do not accept spaces in variable names. Secondly, try to keep names such that you can recognize the actual variable. That is, avoid to put names like x1, x2, x3, since post-analysis, the results from softwares will also be showing these variable names, and then it will become difficult to make sense of the result. I will show you in a couple of minutes what each variable stands for, but even by just looking at the names, you get some idea of what this data is. So this data is about price of houses and other related variables to each house. We will look at these variables in detail in some time. After this top header row, each row contains values pertaining to one observation, and we have a total of 506 observations. The total number of columns we have is 19. We may have received different parts of this data from different sources. Probably one source gave us data of house address and its price. One source gave us data of crime rates in different neighborhoods. In such a case, we need to use a unique identifier which will help us match these two parts. So join all these different parts of data and get it into one single data set with rows and columns, where columns contain each variable and rows contain each observation. Now your data set is ready, but Whenever you are going to share your data or your analysis with anyone, the data should always be accompanied by data dictionary. A data dictionary contains information about the variables in the dataset. So, a comprehensive data dictionary includes the following. It has definitions of all the variables of your datasets. Then it should tell about the unique identifier for each observation. This unique identifier is called the primary key. To match data from another table, if there is a matching key used, that should also be highlighted. If you want to learn more about primary and secondary keys, you can look at our video here. We have shared the link here. This video is part of our another course on database management using SQL. Lastly, if there is a categorical variable in the data, all its values should also be explained. Now let's define the variables of our house pricing dataset. On the left is the variable name as in the dataset. On the right is the brief description of what that variable is. I am going to read these one by one now. So price tells us the value of the house. Crime rate tells us the crime rate in that neighborhood. Resid area stands for proportion of residential area in the town. Air qual gives us the index of quality of air in that neighborhood. Room num is the average number of rooms in houses of that locality. Age is how old is that house, construction in years, how many years ago it was constructed. Dist 1, Dist 2, Dist 3, Dist 4 are 4 distances of that house from the nearest employment hub, because we hypothesize that the price of house will depend on the employment opportunity available near it. Teachers stands for the number of teachers per thousand population in that town. Then we have poor prop. This is the proportion of poor population in the town. Airport stands for is there any airport in the city or not. So this is a categorical variable. It has two values, yes and no. These are self-explanatory, that yes means that there is an airport in the city, no means there is no airport in the city. N hosp beds is giving us number of hospital beds per thousand population in the town. N hot rooms is giving us number of hotel rooms per thousand population in the town. Water body is another categorical variable. It has values like lake, river, both or none, which is giving us whether there is a natural freshwater source within the city or not. Rainfall is giving us the average rainfall in centimeters. Bus ter is a categorical variable which is telling us whether there is a bus terminal in the city. Yes means there is, no means there is no bus terminal in the city. And parks variable is giving us the proportion of land assigned as green land in that town. So with the CSV file and the PDF of PPT attached in the resource section of this lecture, you have with you the data we will be using for our analysis. Note that this data is not real data and is similar to the Boston housing dataset commonly used for analysis. But do not take the result of our analysis too seriously, as this is not actual data. So, whenever we have the data in the tabular format ready with us, we should first look at the descriptives of each variable. The descriptive statistics, as we discussed in another section, are used to describe the data and summarize it. And since we will describe each and every single variable and not relationships between two or more variables, it is called univariate analysis. Uni stands for one, variate stands for variable, so it is one variable analysis. So we can look at the below things as part of the univariate analysis. We can see mean, median, mode. We can see measures of dispersion like range, quartiles, and standard deviations. And for categorical data, we can look at counts of each category. Most software packages for statistics have a very easy way to do univariate analysis for all the variables of the dataset. And when we run it, we see something like this. So for a variable like age, we can have info like mean, median, minimum, maximum, the 25th, 50th and 75th percentile values. Imagine if I arrange all the ages in ascending order. The first value will be the minimum value. The last value will be the maximum value. The 25th percentile value, this 25.75 value will be at 1/4 position. That is 25% of the values will be lower than this value. 29, this 50 percentile value will be at the middle. That is 50% of values will be lower than this. And this 50 percentile value is same as the median also. If you remember the definition of median, 75 percentile value 35.25 is at the 3/4 position. So 75% values are below 35.25, and from 75 percentile to the maximum value is 35.25 to 51. This range is 75 percentile to maximum. So you can observe for this data, the first 25% values are in a very small range of 24 to 25.75. But if you see the last quartile, the last 25% of values are between a huge range of 35.25 to 51. So this distribution is not evenly distributed. Such observations help us identify issues in our data. This whole information for all the variables of the dataset is called the extended data dictionary. Using EDD, we can deduce a lot of things like presence of outliers, presence of missing values, and so on. What are these issues and how we handle them will be covered in the coming videos. In this video, we are going to learn how to do univariate analysis in Microsoft Excel. As I told you in the theory lecture, we want to look at some summary statistics like mean, median, mode of all the quantitative variables. To do that, we use data analysis add-in in Excel. You can find the data analysis add-in in the data menu. If you are not able to see this data analysis option, you need to go to the file menu, click on the options button. Here you have to go to add-ins. In the bottom you have to click on go button, which is for manage Excel add-ins. Here analysis tool pack should be ticked. If it is ticked, you will get this data analysis add-in in the data menu. If it is not, you will not see this. So tick this and click on OK. Before we use the data analysis add-in to do univariate analysis, we need to segregate the quantitative and qualitative variables. As you can see in our table, we have several qualitative variables such as airport, water body, and buster. These variables are categorical. They do not have numerical values in them. We will take out these categorical variables and put them in the end of the data table. So we'll select the whole column by clicking on the name of the column, pressing Ctrl X to cut and Ctrl V in the end to paste it. We will do the same for the other columns. This is the last categorical column. Now these blank columns will be deleted. Just right click on the name of the column and select delete. So all our quantitative variables are from column B to column Q. The columns R, S, T are having categorical variables. So now we will go to data analysis. Here we will select descriptive statistics. This is the option we need to select to do univariate analysis. We will click on OK. We will select the whole input range from B3 to Q509. You can see the shortcuts on the bottom right of the screen which popped up when I pressed them. So input range is entered. Next option is group by. Here we have to select the option where we have our variables. Since our variables are in the columns and our observations are in rows, we want to group them by the columns. Next option is labels in first row. Since our table contains labels in the first row, that is the name of the variable is in the first row of the table, therefore we will tick this checkbox. Then is the option that where do we want the output to be placed. We want the output in a new worksheet, therefore we have selected new worksheet. Then is the checkbox for summary statistics. We will tick it since we are doing univariate analysis and we do want to see the summary statistics. The last two options will be used to get the quartile values. Since by default descriptive statistics option is not going to give us the quartile values, we will put 25 in both of these. So the 25th smallest value is actually the first quartile value, that is the 25th percentile value, and this 25th largest value is going to be the 75th percentile value or the third quartile value. So with all these options set, we will just click on OK, and you can see in a new sheet I am getting the descriptive statistics of all the quantitative variables. Here you can see the mean, standard error, median, mode, standard deviation, sample variance and other such values. The point of looking at this descriptive statistic values is that we want to identify the problems in a dataset. A dataset can have several types of problems. One problem could be of missing values. For example, some variable may be missing few of the values from its data. One problem could be of outliers, that is, some variable may be containing extraordinarily large or smaller values. Although we will see how to identify and handle these problems in the coming videos, here we will see how to identify these problems using the descriptive statistics we have with us. So to identify if any particular variable is missing some values, we can use this count row. All the variables should have the same count, that is, since we have 506 observations in our table, all the variables should have 506 values. If any variable is missing some values, it will have a lesser count. We can see that for the variable n horse beds, we have count less than 506, it is 498. This means that 8 values are missing for this particular variable. We will see how to go and rectify this in our dataset. The second problem could be of outliers. To identify outliers from EDD, there are two possible ways. One is to look at the difference between mean and median. So if there is an outlier, suppose we have an exceptionally large value in some variable. So for such a variable, the mean will be shifted towards the outlier and median will remain almost at the same range. So there will be a large difference between mean and median values. The second method is to compare the distribution of the variable between different quartiles. To compare the distribution in quartiles, we will see the difference between smallest and the first quartile value and the 75th percentile and largest value. So if I look at this price variable, the mean and median are almost in the same range. Mean is 22 point something and median is 21 point something. If I look at the quartile distribution, the first quartile is between minimum and the 25th percentile value. The minimum value is 5 and the 25th percentile value is 10.2. So in the first quartile, we have a range of 5.2. In the last quartile, the 75th percentile value is 43.8 and the largest value is 50. So the last quartile has a range of 6.2. So the difference between the quartile distribution is not very large. This is suggesting that price variable does not have any outliers. So I will highlight the variable which actually has some outliers. If we look at the n hot rooms variable, from the mean and median value, there is not much difference, which may tell us that maybe there is no outliers. Then we look at the quartile distribution. The first quartile is ranging from 10.05 to 10.15, which is a very small range of 0.1. And the last quartile is ranging from 15.19 to 101, which is a very huge range of 85 units. So definitely there are some outliers in this particular variable. How to handle outliers, we will be seeing in a separate lecture. So this is how, by looking at the EDD, we can identify problems in different variables. I suggest that you go through each and every individual variable to identify the issues with that variable. Later on, we will learn how to handle each of these issues. In our data, we need to do outlier treatment also. What is an outlier first of all? Outlier values are the values that appear far away or diverge from overall pattern of a variable. Outliers are usually because some error occurred in the measurement or data entry or sampling process. For example, the error was during data entry and you wanted to enter 1.3 but instead entered 13 because you missed the decimal point. Or it was measurement error and while measuring one of the sensors malfunctioned and gave an erroneous value. Reasons may be any, but it must be handled carefully before feeding the data to our model because these outlying values will otherwise lead to high error variance and lesser prediction accuracy. To find outliers, we should use EDD and visualization tools such as box plots, scatter plots, and histograms. We will see this when we work on the software tools. Once we have identified the outliers, we replace these values with some other values. There are several options of what value we should use to impute outliers. First, let me show you how one single outlier value impacts the data and how can we identify these outliers. These two datasets are same except the one on the right has one outlier value of 300. This leads the mean of right one to be shifted towards this outlier. But median is not changed much. So when the data has outliers, there is a larger difference between mean and median. Also, the standard deviation in such a case is higher. So once we have identified the outliers, we have the following options. We can do capping and flooring. What this means is we find the upper limit and lower limit beyond which we will change the values. So suppose we select the 99 percentile as upper limit and all values larger than this value will be assigned a particular value. I hope you remember what a percentile value is. If you order all the values that are available with you in ascending order, then 99 percentile value is the value which is larger than 99% of other values. So only 1% of values which are larger than this value will be considered as outliers and they will be assigned a different value. Usually we assign a value such as 3 times the 99th percentile value. This multiplier of 3 is a personal choice. Similarly, for lower limit, we can use first percentile value and a multiplier of 0.3. Second method is exponential smoothing. In this method, we extrapolate the curve of 95th percentile to 99th percentile beyond the 99th percentile point and change the values which are going beyond 99th percentile point to fall on this curve. This may seem difficult, but software packages do it straight away. However, I always prefer method 1. Third is the sigma approach, which is popular in the manufacturing industry. In this approach, all values beyond some sigma, for example, all values which are farther from mean by more than 3 times standard deviation, are replaced with the value mean plus 3 times standard deviation. This gives results similar to the first one. So 1 and 3 are actually equivalent. With this, we now know how to identify outliers and how to treat them. In this video, we will learn how to handle the outlying values in our dataset. We have identified from univariate analysis that n hot rooms contains exceptionally large values. These values are outliers and we have to treat them. From the theory lecture, we have told you that when we have an outlier, we cap the values in the variable to a upper limit. To find the upper limit, we find either a non-outlying value and find a multiplication factor, or we use the 99th percentile value and use a multiplication factor to get the upper value. We then change the values of all the outlying values to this upper value. To do the same thing in n hot rooms, we need to first identify those cells which contain the outlying values. To identify the cells, we are going to apply a filter first. To apply filters on the table, we select the top row of our table, then we go to data and we click on this filter option. You can see that these additional small boxes containing a small triangle are coming with each column. These boxes are giving us the filtering and sorting option for this column. Here you can see that all the values of this column are listed in this small box. So if we go to n hot rooms now and open this small box for it, you can see the values are starting from 10.05 and it goes on, and suddenly the values increase from 15.4 to 81.12 and then 101.12. So we have to treat these two exceptionally large values, and to get the value of upper limit we are going to use this largest normal value, which is 15.4, and we will use a multiplication factor of 3. So the value we are going to replace these outlying values is 3 into 15.4, which is 46.2. So to select these two cells, we will first uncheck all of them and go and check these last 3 cells. You can see we have only those observations with us which have these 3 types of values. Now to change the value in this particular cell to 3 into 15.4, we will write is equal to 3 into 15.4. For this cell also, we will change it to 3 into 15.4. So this method of treating outliers, that is, we create an upper limit and change the outlying values to that upper limit, is very subjective. You can choose any non-outlying value, you can choose any multiplication factor to establish this upper value and change these outlying values according to your business need. So with these actions, we have treated the outlying values in our dataset. Now we will take this select all checkbox to get the whole table. Now you can see that we do not have those two exceptionally large values. We have this value. If you think this is still too big, you can treat it further. You can get a smaller value here. For now, we are going to keep this value as the upper limit for our n hot rooms variable. Very often, we find that some values in our data are missing. Now this may happen when you are collecting data from people, asking them to fill a physical form and they do not answer all questions. This may happen because some of the data stored got corrupted. There may be many other reasons. But this results into a serious problem as we cannot run a machine learning algorithm on missing values. Now this leaves us with only two options. Either we remove the entire row which has some missing value. When we have large data set and only few of the observations have missing value, then we can delete those few observations and still have substantial number of observations to train and test our model. But if the number of missing values is high, then removing observations is not advisable. In such a case, we should replace the blank places with some harmless values. Harmless meaning that they should not impact the model much. Such neutral values are values close to the center of that variable. So we can choose mean or median value to be put in these blanks. Here are some most common ways to do missing value imputation. First is to impute with 0. Note that a missing value is not 0. You can simply put a 0 where you have a missing value. But this rarely makes business sense. So if 0 makes sense in any particular scenario, we can do that. Second option is to impute with centers, as this will not have much impact on the model. For example, if we have heights of people as a variable and some of the values are missing in the data, putting 0 does not make any sense. So we can put mean or median height of people in the missing fields. If you have a categorical variable with some values missing, you can assign that category which has maximum frequency in the missing fields. So suppose we have gender data and 90% of them are males, then in the missing fields of the variable, we can safely put male. The third option is again putting in mean value, but instead of using the population mean, if we can make out relevant segments from the data, we can use the segment mean for that segment's observation. For example, if we have rainfall data of different cities, but the data is missing for some cities, instead of using population mean, we can take the mean of neighboring cities or cities belonging to similar region or cities belonging to same state. to fill the blanks. This makes sense since rainfall does not vary a lot among neighboring cities. Therefore, we should use business knowledge so that we can select one of these methods wisely. When we find EDD in any software, the softwares do give us the number of blank values in each variables. We will learn how to fill the blank values in the softwares we are going to use. In this video, we will learn how to handle the missing values in our dataset. Handling missing values is very important since most of the models cannot run if there is some missing value in our dataset. We saw how to find out the missing value using the descriptive statistics option, and we found out that n horse beds variable contains some missing values. To look at the missing values, we will again use these filtering options. If you have not applied filters till now, to apply filters, you have to select the top row of the table and go to data and click on this filter option. Now that you have these filtering options, click on this small triangle of n horse beds, then scroll down and you will find this blanks option. This blanks is giving us all those cells which do not contain any value. So first we will uncheck all of these cells by unchecking this select all button. Then we will tick this blanks option. You can see we get 8 observations which do not have value for n horse bed variable. Now, as we have learned in a theory lecture, depending on the business knowledge, we can use mean, median, maximum or 0 as the replacement for these missing values. For now, we are going to use the mean value of this variable to replace the missing values. To find the mean values, we will again go to the filtering options and select all the values. Select all the values. Here we will write average. So this function will give us the average of all the values. So select all the values and hit enter. So this 7.899 is the average of all the values of n horse beds variable. We will use this value to replace the missing values. So copy this value, then click this icon and select only the blank values and paste this value in each of these blank cells. But while pasting, you have to paste this as values. So the second option in pasting options is values. Click on this to paste the value of this. Otherwise, you will paste the formula here, which will give you the wrong value of the average. So right click on the cell, go to paste options and select this second image of paste as values. So now we have replaced all the blank values with the mean. If I remove the filter and select all, now if I go, there will be no blank value in it. So we have handled the missing values in this n horse beds variable. If in your data set there are other variables which have some missing values, you need to treat all those variables, apply the filter and select the blanks in that column. Change the values of those blanks to mean, median, max, whichever is the business scenario for those missing values. In this video, we will learn about variable transformation. As you can see in our dataset, we have 4 distance variables. These distance variables are giving us the distance of the house from 4 different employment hubs. Now keeping 4 distance variables in our dataset is over-representing the importance of the employment variable. We need to transform these four variables into one single distance variable, which can represent the employment opportunity near that house. There can be several ways to transform these four into one. Either we can choose the minimum of the distance, or we can choose the maximum of these four distances, or we can just take a average of these four distances. Usually we have to take into account the business scenario in which we are to decide which transformation method we are going to use. Here I'll use the mean method, that is I'll replace all these four variables by the mean of these four variables. Depending on your business scenario, you have to take the decision for your problem. So I'll add a new variable. To add a new variable, I'll need a new column. So I right clicked on the column name and I inserted a new column, and I'm naming it average dist, avg underscore dist. Now in this variable, I'll put the average value of the other four variables. So this is average of these four variables. Hit enter. Now to extend this formula for other cells, you can just double click on this bottom right corner of this cell, and this formula will be extended to other cells below this cell. So this value of 4.08 is the average of these four distances: 4.35, 3.81, 4.18 and 4.01. Similarly, the average distance in the next observation is the average of next four distance variables. Now that we have the average distance variable, we do not need the other four distance variables. So therefore, we will be deleting those four distance variables. But before we delete these four variables, we first need to change the value in this cell from this formula to the actual value. So we will select the values in all these cells, copy them by pressing Ctrl C, then right click on this cell and paste these as values. Now we have the exact same value in this cell, but instead of the formula, we have the value here. Now if I delete these four columns, it will not impact the value in the average distance column. So I have selected those four columns and clicked on delete option. So this is how we identified variables which need transformation. We transformed them into a new variable and we deleted the old variables. Next important thing we need to know is how to handle the categorical variables in our set of independent variables. If you remember, in our data set we have variables like airport, which has values yes and no, and there is a variable called water body which has values such as lake, river, etc. Now regression model works on real numbers. It will not understand a non-numerical variable such as airport. How can we handle this problem? It is simple. We just need to assign a numerical value to each of the categories of that variable. If the category names are numbers, regression model can run. But we cannot assign any number to the categories as this will impact the model. We need to follow a proper process. So this process of properly creating a dummy variable which will represent an actual variable containing non-numerical values is called dummy variable creation. So why we do it? Because regression analysis cannot handle non-numeric data. And how we do it? We first create a new variable or set of variables, that is the dummy variables. Then these new variables are given values of either 0 or 1 and not anything else. But why? Why not we assign values like 1, 2 and 3 etc.? Let us look at the categories in this example for clarification. On the left, I have students and their favorite subjects. On the right, I am coding these subjects. The first step of dummy variable creation is creating dummy variables. How many dummy variables do we need? Remember this. The number of dummy variables required to replace a variable is number of categories in that variable minus 1. That is, if there are 2 categories, we need 2 minus 1 dummy variables, that is only 1 dummy variable. If we have 3 categories, like in our example, we need 3 minus 1, that is 2 dummy variables. So I have 3 subjects here: science, English and maths. So I have created 2 dummy variables, one for science and one for maths. Science has value of 1 if the subject is science, else it has value 0. So if you look at the first two, it has science as 1, and the other two where the subject is English and math, it has value 0. Math has value 1 if the subject is math, else it has value 0. So the fourth row has 1 in the maths column and all the other rows have 0. This means if both are 0, then the subject is English. So the third row has both 0, which is representing the third subject. Clearly, these zeros and the ones are representing each category of the favorite class variable. Now to answer the question why we created 2 dummy variables when we could have created a single one with values such as 1 for science, 2 for maths and 3 for English. This is because 1, 2, 3 have more meaning, that is, say 2 is actually twice of 1. But maths is not higher than or more than science. Maths, science and English are nominal data. It just says the name of the favorite subject. So we cannot assign numerical values which can be ordered. Whereas when we are assigning 0 and 1, it only represents true or false or yes and no. Therefore, we create n-1 dummy variables. The value of each dummy variable is 1 for one single category, and the nth category has 0 value for all the n-1 dummy variables. How to interpret the results of regression analysis containing dummy variables coded like this will be discussed after we run the regression on our data. In this video, we will learn how to handle these categorical variables by creating dummy variables. As told in the theory lecture, whenever we have categorical variables, we need to transform them into dummy variables containing numerical values, since our regression model cannot handle non-numerical values. So we have these 3 categorical variables: airport, water body and buster, which contain non-numerical values, and we will look at their categories and determine the dummy variables to be created. So I have the filtering options here. If you want to apply filtering options, you have to select the top row and go to data menu and click on this filter option. Here, if I open the filtering options for the airport variable, you can see that it contains 2 values, yes and no. If I select yes, that is I uncheck no, the number of yes in the observations can be seen by selecting all the yeses, and you can see the count below, it is 279. So out of 506 observations, I have 279 yes. So there are 2 categories in the airport variable. As told in the theory lecture, we need n-1 dummy variables. N is 2, so we need only 1 dummy variable. So we'll create a new column. We'll name it airport underscore yes. It will contain 1 whenever the value of airport variable is yes, and it will contain 0 whenever the value of airport variable is no. So here we need to use if function. We will write if the value in the corresponding cell is yes. In double quotation marks, we will write yes. If this is true, we want it to be 1. If this is false, we want it to be 0. You can see we get 1 when the airport value is yes. If I drag it to all the other cells below this cell, I am getting 1 zeros. Wherever there is no, I am getting a 0. Wherever there is yes, I am getting 1. So the dummy variable for airport categorical variable is ready. Before deleting the airport variable, we need to change this formula to values. So we will select all the cells, copy them, then we will right click and paste as values. Now it has value instead of the formula. Now I can delete this column. So we have airport dummy variable instead of the airport categorical variable. The next categorical variable is water body. This variable contains 4 categories. One is lake and river, one is none, and the last one is river. Since it has 4 categories, we need 4 minus 1, that is 3 dummy variables. So we will keep 3 dummy variables, one with name water body lake, one with name water body river, and the last one with the name water body lake and river. So we need to insert 3 different columns. In the first column, I'll take water body underscore lake. This will have value 1 if the value in the corresponding water body variable is lake, otherwise it will have value 0. So we'll write is equal to if this cell has value lake, then it should be 1, else it should be 0. Extend it to other cells in the column by double clicking on the bottom right corner of this cell. Now in the next column, we'll take water body river. Here if the value is river, then it will be 1, otherwise it will be 0. You can see that whenever the value is river, the water body river dummy variable contains a value of 1. Last is water body lake and river. In this variable, if the value is lake and river, then it should be 1, otherwise it should be 0. Double click on the bottom right corner to extend it to other cells. So we have 3 dummy variables to represent this one categorical variable since it has 4 categories. Now we will select the values in all these 3 columns, copy them, paste them as values, and we can delete the water body variable now. The last categorical variable is bus terminal. It has only one category, which is yes. If a categorical variable has only one category, it is not really a variable. It can be treated as a constant, and we do not need any dummy variable to represent this variable, since in n minus 1, if n is equal to 1, then the count of dummy variable comes to 0. So we do not need this variable at all. We will straight away delete this variable. So with this, our data set has no blank values, it has no outliers, and all the categorical variables are converted to numerical values. With this data set, we are ready to run our analysis. So when do we say that variables are correlated? When the values of those variables fluctuate together, we say that variables are correlated. They are positively correlated if one variable almost always increases when the other one increases, and negatively correlated if one decreases when the other one is increasing. For example, if you think logically, there should be a positive correlation between calorie intake and a person's weight. That is, if you increase your calorie intake, you should have more weight, and if you reduce it, you should have lesser weight. Similarly, amount of time one studies should impact the GPA of that student. So this means they should have some correlation as well. However, selecting variables with no commonality results in non-correlated variables. For example, a dog's name and the type of biscuit the dog will prefer will not be correlated. So we say for such scenarios correlation is nearly zero. You can think of any bizarre combination of two variables, and most probably those should have low correlation. The quantification of correlation is called correlation coefficient. There is a statistical formula to compute the correlation between two variables. Although the formula is simple, but since we will never find out correlation coefficients for our data manually, we will always be using some softwares to do this. We will not be discussing the formula here. However, just note certain characteristics of correlation coefficient. First, its value is between -1 and 1. So plus 1 means there is 100% positive correlation, and -1 means 100% negative correlation. Secondly, zero value of coefficient indicates that there is no relationship between the variables. You can see the graphs here. The first one shows positive correlation, that is, if one value on the x-axis is increasing, the value on the y-axis is also increasing. The middle one is representing no correlation. Even if you increase the value of one of the variables, the other one does not change. The third one is showing negative correlation, that is, if you increase value of one variable, the value of other variable is going down. As a rule of thumb, if we find the value of correlation coefficient as less than 0.1, we say that there is very low correlation between the two variables, and if we find that it is more than 0.8, we say that it is very high correlation between the variables. It is important to note the difference between correlation and causation. Correlation is just representing whether the values in two variables for our sample data set are moving together or not. But it does not tell us anything about cause-effect relationship between the two. We cannot say that because correlation coefficient is high, that increase in one variable will lead to increase or decrease in the other variable. Take this example. This example shows the values of US crude oil imports from Norway and the number of drivers killed in collision with railway train. You can see from this graph itself that both of these values are going hand in hand. If you find out the correlation between these two values, this coefficient is coming out to 0.95, that is nearly 95%. Such high value of correlation may lead you to think that these two variables are highly correlated and increasing one of them may lead to increase in the other one. That is not the case. These two are completely random two variables and they do not have any relationship amongst themselves. So to establish cause effect relationship, one of the most common ways is to use the intuition, to look back at the business knowledge and to find out whether the change in one of the variables actually impacts the change of the other variable or not. The other method is a difficult one. It is setting up a scientific experiment where we manipulate the variable in a controlled environment and see the impact on the other variable. We'll not be covering that in this lecture series, but just in case you are doing a controlled experiment, that is one of the options that you have. So for our data set, we'll be depending on the business intuition to establish causation. When you have a data set with multiple variables, we may want to see the correlation coefficient for each pair of variables. There is a tabular format in which we take all the variables on top like this and all those variables on the left also like this, and then for each combination of these two variables, say for this never to try to evade taxes and always to vote in elections, so this cell, so this combination of these two variables, correlation coefficient is mentioned in the corresponding cell. This table is called correlation matrix. If you look at this matrix, these diagonal values are actually the correlation of that variable with itself. So basically, whenever this variable increases, this is also increasing. Whenever this is decreasing, this is also decreasing, and they are going perfectly hand in hand. That's why this value is always going to be 1. All the values on this diagonal are going to be 1. And this value, which is giving us the correlation between always to vote in elections and never to try to evade taxes, this 0.94 value will also come here because these two variables are also present as rows and columns for this cell. If you look at this matrix carefully, this matrix is basically having a mirror image of itself about this diagonal. So this particular cell is same as this cell, this particular cell is same as this cell, this is same as this cell. So basically it is a mirror image about this diagonal. Once we get this matrix, we can easily see the patterns in our data. That was the primary goal of making this matrix. Another useful feature of this matrix is that you can quickly find out which two independent variables are highly correlated. But why are we trying to find out correlation values between two independent variables? We are doing this because whenever there is correlation, the two correlated variables are moving together. Therefore, if one of them is linearly related individually with the dependent variable, then the other one will also show linear relationship with the dependent variable. But when you will take both the variables in your model and model has to assign relative importance to each of them, really tedious job for the model. Every time you will show your model a new sample of data, it will assign different regression coefficients to these variables. This problem for the model is called multicollinearity. Therefore, it is important that we identify highly correlated independent variables and remove one of the two so that multicollinearity can be avoided. But which one of the two would you remove and which one you would keep? First, try to keep the one which makes more business sense. If both make business sense, look at the correlation coefficient of both with the dependent variable. Whichever is higher, you may want to keep that one and remove the other one. If both of them are having the same correlation coefficient, then you may go and pick the variable for which the data is easier to get. So this is the use of correlation coefficients and correlation matrix. In this video, we will learn how to create a correlation matrix which gives us the correlation between different variables of our dataset. To create a correlation matrix, we will use the data analysis add-in which contains the correlation matrix option. So we'll click on data analysis. Here you can see the analysis tool which is correlation. Click on OK. In the input range, we will select the whole table. To select the whole table, you can use the shortcut of Ctrl Shift plus arrow keys. So first is the input range, which is the whole table. Second is grouped by, which is again columns, since columns contains our variables. Next option is labels in first row, which is true, since our first row of the table contains the name of the variables. And lastly, it is asking us where do we want our output. We want our output in a new sheet. So that is selected and we can click on OK now. So here is the correlation matrix for all the variables in our dataset. You can see that all the variables are listed in rows and columns both. So in the first column and in the first row, we have the variable names. This first cell is giving me the correlation between the first column, which is price, and the first row, which is again price. So since it has the same variable on both the sides, the correlation of that variable with itself is 100%, which is 1. So you can see the whole diagonal is intersection of the same variable with itself. That is why it is having the value of 1. In this second value, it is the correlation between crime rate and the price variable, and the value of this is minus 0.46. That is, if crime rate is increasing, price values are in general decreasing, and if crime rate values are decreasing, price is increasing. Similarly, we get the correlation values of all the combinations of variables. The corresponding second value on the row is empty because it is again the correlation between price and crime rate, which is same as this value. So that is why the upper half of this diagonal is empty and the lower half is filled. Now, as told in the theory lecture, we can see that which all variables have very high correlation with the dependent variable. This will help us identify which all variables are important and are expected to have some impact on the response variable. So since this first column is the price column, which is our dependent variable, we can color code this using conditional formatting. In home menu, under these conditional formatting, we can use color scales. So if I use this particular color scale, a dark blue color would mean a very high positive correlation, a dark red color would mean a very high negative correlation, and no color or white would mean that there is very less correlation between these two particular variables. So from this, we can say that we expect room num, teachers, poor prop, all these variables to highly impact the price, whereas n hot rooms, water body lake, water body river, water body lake and river, all these variables to have a very little impact on the price variable. So this is how we interpret the relationship between independent and dependent variables basis their correlation matrix. We also need to see the correlation values for all the pairs of independent variables. We need to establish that our independent variables are not correlated amongst themselves. This is because if the independent variables are highly correlated, we face a problem named multicollinearity in our analysis that may impact our final result. So we need to identify those variable pairs which have high correlation and delete one of the variables of that pair so that we do not encounter multicollinearity. So to identify pair of variables which have high correlation, we will again use conditional formatting. We will select this, we'll go to the conditional formatting options and we'll give a new rule. In this we will select the rule that format only cells that contain cell value not between minus 0.8 and plus 0.8. Wherever this is the scenario, we want that cell to be filled with green color. So wherever the cell value is not between minus 0.8 and 0.8, which means that the cell value is very high, there is very high either positive or negative correlation between that pair of variables, there the cell should be colored green. So we'll click on OK. You can see that only this pair of parks and air quality is colored green. That is, the value of parks and air quality is highly positively correlated. To prevent multicollinearity, we need to delete either of these two variables. Now, which variable to delete will depend on the business scenario. You have to go back and check the business knowledge on which of these two variables is more important to our analysis and which can be dropped. Alternatively, you can also consider the fact that collecting data for which of these variables is easier. If there is no difference between these two variables in this sense, you can opt for that variable which has higher correlation with the dependent variable. For example, here air quality has minus 0.42 correlation and parks has minus 0.39 correlation. Since air quality has a higher value of correlation with the price variable, we'll keep air quality and we will delete parks. So we'll go to our house pricing data and we will delete the column which contains the value of parks. So this is how we draw the correlation matrix and analyze it using conditional formatting in Microsoft Excel. Now we are going to start with linear regression. It is a very simple approach for supervised learning. Linear regression has been around for a long time and is still a useful and a widely used statistical tool. Also, it is a very good starting point for machine learning, as many of the newer and fancier approaches of machine learning can be seen as an extension of the linear regression method only. Therefore, it is really important to have a solid understanding of linear regression before you move on to complex learning methods. In the coming videos, we will learn the key concepts behind linear regression model and then learn the least square approach, which is the most commonly used approach to fit a linear model. Let us go back to the house pricing data. The prediction question asked was, how accurately can I predict the price of a house given the values of all these variables? The inferential question that we were asking is, how accurately can we estimate the effect of each of these variables on the house price? So we are going to find the answers to these two questions using linear regression. Now, simple linear regression is a straightforward approach for predicting y on the basis of a single predictor variable x. So if you take only one predictor variable, it is called simple linear regression. If we assume linear relationship between x and y, mathematically it can be written as y is approximately equal to beta 0 plus beta 1 x. It is nearly equal to because the value of y that our model will give may not be exactly equal to the value in our observation. We will come back to this thought later. Here, let us select only one variable from the data set to predict price of the house. Let us say I choose average number of rooms for this simple model. So we will regress house price onto the number of rooms by fitting the model price is nearly equal to beta 0 plus beta 1 times room num. Here, beta 0 and beta 1 are the unknown terms which are known as model coefficients or model parameters. For the particular case of simple linear regression, beta 1 is the slope and beta 0 is the intercept. Once we use the training data to estimate these two parameters beta 0 and beta 1, we will be using this hat symbol to denote estimated parameters from our data. So we will write price is equal to beta 0 cap plus beta 1 cap times number of rooms. So for estimating the values of our parameters, we will be using the data points in our data set. If you remember, our house pricing data set has 506 observations. This number of data points for general purpose will be denoted by n, small n. So small n is 506 for our data set. What this means is we have 506 pairs of x and y values, and our goal is to obtain coefficient estimates beta 0 cap and beta 1 cap such that the linear model fits the available data, such as y1 cap is equal to beta 0 cap plus beta 1 cap x1, and if you generalize it for any I, it is yi is nearly equal to beta 0 cap plus beta 1 cap xi. In other words, we want our estimated line to be as close to these points as possible. One method for measuring this closeness of our line is called the least squared method, which we will discuss now. Once we run the model and get a line, the line will be predicting a value of y at each point I. This predicted y value will be denoted by yi cap. Now we do have the actual values of y at each of these points. The difference between these actual values and the predicted value is our miss. This is the residual and it is denoted by ei. As you can see in the graph, using the training data that we had, we have fitted a line using the beta 0 and beta 1 that we calculated, and this line is drawn here in the blue color. Each of these points is also plotted. Some of these points are exactly on the line, but most of them are missing. The distance of that point from the line is the residual. At some points this residual is positive, at some points this is negative. When we are taking out the total residual of this sample, we cannot straight away sum them up because some are positive and some are negative. Therefore, we will define a new quantity called residual sum of squares. Now since RSS is summing the squares of each residual, it is representing the total error. In this formula, you can see that for each of the point, we are subtracting the actual observed value from the predicted value and then squaring it, and we are doing this for all of the points. Now we have the total error of our predicted line and we want to minimize this error. So using calculus and matrix algebra, we will get these formulas for beta 0 and beta 1 for which this error is minimized. So this approach is called least square method because we are minimizing the squared error, squared sum of errors. So this RSS value we are trying to minimize. So by differentiating and putting it to 0, we'll get these values of beta 1 cap and beta 0 cap. For this value, for these values of beta 0 and beta 1, the calculated sum of squares will be minimum. So beta 1 is summation of xi minus x bar. If you remember, x bar is the mean of the sample. So for each data point, we will find out this difference of each point from its mean, and then we'll multiply it with the difference of each y variable with its mean. We'll sum this product for all the points and we'll divide it by the difference of x from its mean squared added over all points. Similarly, for beta 0, it is mean value of y minus beta 1 cap times mean value of x. So we have mean value of x and mean value of y. We first need to calculate the beta 1 value. When we put beta 1 value in this formula, we will get the beta 0 value. So using these formulas for simple linear regression, you can get the beta 0 and beta 1 values. So for our model, where we selected house price as y and room num as x, if I run this model in a software, I get this result. I have highlighted the beta values in this blue box. This intercept is beta 0 and room num is the x variable, and this is giving the coefficient of this variable. So this is beta 1. So beta 1 is coming out as 9.09 and intercept is coming as minus 34.69. In other words, this means that if I increase the number of rooms by 1 unit, the price of house will increase by 9 units. What is the meaning of all these other values? That we'll be learning in the coming videos. One thing to note here is you do not need to remember these formulas because the software packages will be doing it for you. As you saw in this video and you will see in the coming videos, we'll be telling you the mathematical concept behind the theory and discussing those mathematical formulas also. Keep in mind that you do not need to remember these formulas. You just need to understand the concept behind them, the intuition that I will tell you that will help you interpret the result. That understanding of result is very important, but you do not need to memorize these formulas since you will be using a software package which will be applying all these formulas and getting the results for you. So preparing the data is important, running a model is important, and interpreting the data accurately is the most important. Remembering formulas is not important in machine learning now. Also, even if you do not understand the mathematical part of this, don't be worried. You can still run a machine learning model and you can use the results in your professional life. But I highly recommend that you go through all the lectures very carefully to understand the core concepts behind all these machine learning methods. In this video, we will assess the accuracy of these coefficients beta 0 and beta 1 that we have calculated. I will start by restating the situation that we are in. In the world, millions of house transactions were happening. We picked a small set or a small sample of 506 such observations and decided to identify the relationship between house price and number of rooms. When I use the formula shown in previous video, we get the values of beta 0 and beta 1. This line is minimizing the squared error on the sample of 506 points. If we had selected some other 506 observations, we may have got some other values of beta 0 and beta 1. If we take all the million observations of the world and then get a line, this line will be called the population regression line. This line may or may not be same as the sample regression line. You can see in this graph, this blue line is the sample regression line, which is minimizing the error on these data points, these sample data points. But this red line, which is the population regression line, which would have come if I would have solved the least squared error for all the data points of the population. These two lines are not same. Now the problem is this: We do not have all the observations, therefore we cannot get population regression line. We have sample data, so we can get only the sample regression line. We want to use the coefficient of sample regression line as an estimate for the population regression line. How far off will the sample estimates, that is beta 0 cap and beta 1 cap, will be from the population coefficients, which are beta 0 and beta 1? For this, we will use a quantity called standard error of beta 0 and beta 1. The standard error of beta 0 and beta 1 is calculated using these formulas. Again, I am showing you these formulas and discussing the intuition behind them. You need not memorize them or know their derivation for practical purposes. But since these quantities will be part of the output of the model from our software, we need to understand their meaning. So in this formula, there is a sigma square. Sigma square is the variance of population residuals. Remember we discussed residuals. Residual is the value which is the difference of actual y from the estimated y of the population. Sigma square is the variance of these values for all the data points of the population. Since population regression line is not known, this sigma square is also not known. We need to estimate it from our sample data too. This estimate is given by this formula, which is RSC is equal to under root RSS by n minus 2. Here RSC is called residual standard error. RSS is the residual sum of squares. We discussed this in the last video, which is sum of all the e squares. So for all the data points, we get the errors, that is the residuals. We square them and we add them, that is the RSS. We divide RSS by n minus 2. N is the number of observations. So for our data set, it is 506. We'll divide it by 506 minus 2. When we find its under root, we get residual standard error. We'll use this residual standard error as a proxy for sigma. Also notice that if x is more spread out in this formula of beta 0 and beta 1, standard error of beta 0 and beta 1 will be small, which intuitively means that we have more leverage while estimating the slope in such a case. Now, what is the practical takeaway from the SE calculations? Standard error will be used to give us a confidence interval. That is, for linear regression, there is a 95% chance that true value of beta 1 lies in the interval beta 1 cap minus 2 times standard error of beta 1 to beta 1 cap plus 2 times standard error of beta 1. So within this interval, where lower value is this and higher value is this, we are 95% confident that the actual beta 1 lies in this interval. Similarly, for beta 0, the 95% confidence interval will be the estimated beta 0 minus 2 times standard error, this standard error of beta 0, and the higher value will be beta 0 plus 2 times standard error of beta 0. To summarize, what we have done here is we had two lines. One line we got from the sample regression that we did. The other one is a hypothetical line, which is the true line between the population of all the points. We wanted to show whether we can approximate this sample line as the population line. For that, we found out the confidence interval within which the population coefficients will lie. So the beta 0 of the population line will lie between these two values that we get from the sample regression, and the slope of the population regression will lie between these two values of the sample regression. And we have assigned a probability of how confident we are. We are saying that there is a 95% chance that the population regression coefficients lie within these intervals that we found out using sample line. Another use of standard error is to establish that whether x and y actually have a relationship or not. In a linear model, this relationship is given by beta 1. We are saying that y is beta 1 times x plus constant. So if beta 1 is 0, it means that there is no relationship. If there is no relationship, then the variable x cannot be used to predict y. So we need to show that the probability of beta 1 being 0 is negligible. Let me tell you the concept first, and after that I'll show you the way how you will find it in every other statistical book. The concept is this: beta 1 has some value that is the most probable value found out by the formula we saw in the previous videos. Now if we want to say that we are sufficiently confident that it cannot be 0, it has two parts to it. First, most probable value should be far from 0, and second, the standard error of beta, which is giving us the interval in which beta true lies, should be small. So basically we want 0 not to lie in this whole interval in which beta lies. I hope you get the idea. Let's do it the proper way now. This method is called hypothesis testing. We will construct two hypotheses. One is H0, that is there is no relationship between x and y, and H alternative, which is written as HA, that there is a relationship between x and y. So H0 is beta 1 is equal to 0, HA is beta 1 is not equal to 0. And we want to disprove H0. To disprove H0, we will calculate something known as T statistic, which is given as T is equal to beta 1 cap minus 0 divided by standard error of beta 1. So you can see what this T is representing here. In numerator, it says how far beta 1 is from 0, and when you divide it by standard error, you get the distance is how many times standard error. So using this formula, we'll get a t value. Now we want this t value to be large. By the way, it is called t value because it is based on t distribution, which is similar to normal distribution. Basically, t distribution is another probability distribution, and if you have t value, you can get the probability of observing any value equal to absolute t or larger. The probability that you will get from this distribution is called p-value. Now this p-value has meaning. We can interpret p-value as follows. Small value of p will mean that it is highly unlikely that there is no relationship between predictor and response, which means that we can reject the null hypothesis and declare that there is a relationship between x and y. Typically we use a value like 5% or 1% as the cutoff value for p. That is, if p is less than 0.01, then the variable x is significantly impacting y. Let us look at the results of our sample. Note that this is the result which we have received from the software package that we are using in the course. There is a separate video where you will learn how to run this analysis and get this result. I'm just discussing the result here as an example to all the theory that we just covered. So in the last video, we had just seen the beta 1 and beta 0 values. This intercept is the beta 0, and this room num variable has this slope. This 9.09 is the beta 1 for this variable. The first thing that we covered is the standard error for beta 0 and beta 1. The formula that I showed you earlier was used to calculate the standard error of beta 0 and beta 1. How the standard error can be used is, you can make this statement that for the sample of 506 observations, the beta that you calculated for minimum error was 9.09, but you are 95% confident that for the global data of house pricing, the beta 1 will lie between 9.09 minus 2 times 0.41 to 9.09 plus 2 times 0.42. So this interval is giving you that the estimated betas that you have here can be used to make this statement that the true regression coefficients will lie in an interval given by this standard error. The next thing we discussed was the t value and the p value. This t value and p value, we said that we have one hypothesis which is saying that there is no relationship. To disprove that hypothesis, we calculated a t value which was given by this formula. So to get t value of this beta 1, we will put the beta 1 cap value divided by the SE. So 9.09 divided by 0.41 gives you this t value. So corresponding to this t value, we calculate a p value which is written as probability of getting a t value which is greater than equal to this t that we calculated. This probability value is coming out to be very small. It's an exponential with a power of minus 16. So this value is very small. So if this value is very small, we can say that it is unlikely that there is no relationship, which means that there is some relationship, and therefore we are confident that room num variable is impacting the house pricing, and the relationship between them is given by this coefficient. So the takeaway from this lecture is we have beta 1 and beta 0 values calculated for the sample. We calculated a standard error which is helping us in determining two things. One is what is the range in which the true value of beta 1 and beta 0 will lie, and the second thing is whether there is actually a relationship between these predictor and the response variables. To establish that there is a relationship, we calculated a t value using these two things. Using the t value, we calculated a p value, and if this p value is less than a threshold of 1% or 5%, whichever you like to use, then we say that there is a relationship. So for our model, there is a relationship of house pricing with room num, and that relationship is this beta 1, which is 9.09. In this video, we will assess the accuracy of the model that we have created. Now we have established the relationship between x and y, but we want to know how well does the predicted y values fit the actual y values. So to assess the quality of it, we will look at two related quantities. One is residual standard error and the other is called R-square. Let us first look at residual standard error. We saw earlier that residual standard error is under root RSS by n minus 2, which can also be written like this as a summation of square of difference between actual value and predicted value. Roughly speaking, RSE is the average amount that the response will deviate from the true regression line. As you can see in the result shown below, this is the result we got when we ran the model in our software. It is straight away giving us the residual standard error, which is 6.597 for this model on 504 degrees of freedom. This 504 we are getting from n minus 2. N is 506. So n minus 2 is 504, and this is called the degrees of freedom. So for these many degrees of freedom, we are getting a standard error of 6.97. In other words, even if the model was correct and true values of beta 0 and beta 1 were known exactly, the predicted value of house price from this model will still be off by 6.597 units on an average. Therefore, RSC can also be considered as a measure of lack of fit of this model to the data. So this 6.597 value is telling you on an average by how many units your predicted value is missing the actual value. Next is the R-square statistic. The RSC provides an absolute measure of lack of fit, but since it is measured in the units of y, it is not always clear what constitutes a good RSC. So R square provides us with an alternative. R square is a proportion, the proportion of total variance explained by our model. So it always lies between 0 and 1. Here is the mathematical formula for R square. R square is TSS minus RSS upon TSS, where TSS is total sum of squares and RSS is residual sum of squares. TSS is measuring the amount of variability inherent in the response. That is, for our house prices data, the price of each house itself is varying about the mean house price. So if you find the difference of actual house price from the mean of the house price, square these values and add them up, you get total sum of squares. So this total sum of square value is giving you the total amount of variability in house price. How much of this is explained by the model that we constructed? For that we will use RSS. RSS is measuring the amount of variability that is not explained by our model after regression. Hence, TSS minus RSS is giving us the variability of y which is explained by our model. Therefore, R square measures the proportion of explained variance from the total variance. R square value close to 1 indicates that a large proportion of the variability in the response variable has been explained by the regression model. If it is close to 0, it indicates that regression did not explain much of the variability. This can occur either because our linear model is wrong or because linear was not the right choice for this relationship between x and y, or both of these reasons. For our model, the result given by the software package is that residual standard error was 6.59, R squared value is 0.48. So it is somewhere between 0 and 1. Nearly 50% of the variability of the response variable is handled by the model that we constructed. There is another value which is called adjusted R squared, which you can see from the model result. The difference between this R squared and this adjusted R squared is that in adjusted R squared, we'll be also taking into account the total number of variables which are actually impacting the model. The reason behind doing this is, if you keep on adding variables to your model, R square value simply keeps on increasing. Even if the variable is not significantly related with the response variable, still the R square value will increase by a small amount. So the adjusted R squared is a modified version of R squared that has been adjusted for the number of predictors in the model. The adjusted R squared increases only if the new term improves the model more than would be expected by chance. It decreases when the predictor improves the model by less than expected by chance. So adjusted R squared is a more preferred term over R squared. Now we have a value of R square, but what value of R square will be considered as a good value of R square? This will generally depend on the type of application that you have. If the data is coming from a science experiment and the relationship is supposed to be actually linear, in such a case R square should be very close to 1. But if it is a marketing data and we are missing a lot of unmeasured factors, and the linear assumption is also a rough approximation of the relationship, the residual errors are going to be large. In such a case, even smaller R-square values can be acceptable. Generally, R-square greater than zero point 0.5 can be considered as a good fit model. In this video, we are going to run simple linear regression. That is, we will use only one predictor variable to predict the value of price. The predictor variable we are going to use is room num, that is number of rooms in the house. And using the value of room num, we will try to establish a relationship between room num and price. We did this earlier also, where we created this trend line and saw the equation and the R square against this trend line. Now we will run the proper regression analysis and see its results. So we will go to data analysis options. Here we will select the regression option and click on OK. The input Y range is the response variable which is in B column. So we will select this whole column. The input X range is our room num column. Our data has labels, that is the first row of the column contains the variable name. Next option is where we want our output. We want our output in a new sheet. And we do not need to look at the residuals for now. So we'll just click on OK. And we get the result of linear regression between these two variables in this new sheet. You can see that the R square value is coming out to 0.4848. This is the same as the one we got when we plotted this trend line. The beta values is in this column. So this is beta 0 against intercept, and this particular cell is containing beta 1 value, which is the coefficient of room num variable. So a value of 9.09 is telling us that if I increase the room num variable by 1 unit, it will increase the house price by 9.09 units. So using these two beta values, we can estimate the equation between price and room num. We will understand the meanings of all these other parameters in the coming videos. We saw simple linear regression with only one predictor variable. However, in practice that is rarely the case, and we usually have more than one predictor variable. Even in our house pricing data, we have 16 variables left after data pre-processing. Let us now try to extend our analysis to accommodate multiple variables. Mathematically, for multiple linear regression, the equation can be transformed as below. Y is equal to beta 0 plus beta 1 times x1, the first predictor, plus beta 2 times x2, the second predictor, and so on till the last predictor. Here P is giving us the number of predictors, and eta, this last term eta, is the error term. The error from of this predicted Y from the actual Y. And for our data set, this equation can be modeled like this. Price is equal to beta 0, which is a constant, plus beta 1 times the first variable, plus beta 2 times the second predictor variable, which is poor population, and so on till the 16th variable. So for any jth predictor, beta of that jth predictor is giving the average effect of 1 unit increase in the value of that predictor on Y, with the assumption that we are holding all other predictors fixed. For example, if we increase poor population by 1 unit, price will increase by beta 2 units. If we increase average distance by 1 unit, price will increase by beta 16 units. So the coefficients are giving us the amount of increase in the response variable. So when we are estimating the regression coefficients in a multiple linear model, the logical flow remains the same. We first get the residual sum of squares by this formula. So this is the square of difference between the predicted and actual values, and for all the data points it is summed. So we try to minimize this value, this RSS value. We will again use calculus and matrix algebra to get the coefficients, but the multiple regression coefficients are a bit complicated, so we are not providing them here. Our software will be handling that part again for us. Below I have given the result of the multiple linear regression model run on our dataset. It includes all the predictor variables, the beta estimates, the coefficients, then the standard error. We saw how to calculate standard error before we did simple linear regression, and the corresponding t and p values. Against these p values, depending on their significance, we have these star marks. So we said that we can have a threshold of 1%. If we have a threshold of 1%, we'll get 2 stars. If we have a threshold of 5%, we'll get 1 star. So these two are having a confidence interval of 95%, and these three are having a confidence interval of more than 0.1%. And in the end, these are the values for the complete model. So these are values for individual variables, and these values are for the complete model. So here is the multiple R-squared, which is 0.72. That is 72% of the variance in the values of Y, in the values of house price, is explained by our model. Adjusted R-square is taking into account the number of variables. So the number of variables is 16. So it is taking into account that we have 16 variables. So correspondingly, the adjusted R-squared is 0.71, which is nearly the same as R-squared. And we can say that this model is pretty good in explaining the variance of Y. Remember that this is just the result. In a separate video, I'll show you how to get this result, how to run a multiple linear regression model in the software package. And there we'll be discussing the whole result again and the meaning of each and every coefficient and the p-values and this R-squared and F statistic. The aim of showing you here is that when we run a multiple linear regression, this is the type of result that we get. We get the beta coefficients and their corresponding p-values for each of the predictor variables, and we get some other values which are for the whole model. So you would have noticed that there is one value of this output that we have still not discussed, and that value is called F statistic. And in this video, we'll be discussing about F statistic. Now, if you see in the result for each of the coefficient, there is a corresponding t value which is telling us whether each individual predictor is related to the response. I am talking about these t values and probability values, these two columns. So since at least one of them has a small p value, here we have 6 of them. So since at least one of them has a small p value corresponding to their t value, we may think that surely at least one of the predictors are related to the response. Therefore, we will say that there is a relationship between response and predictor variables. That is, not all of the coefficients of the variables, that is beta 1, beta 2 up to beta p, are 0. So all of them are not 0. So this argument may sound okay, but it is actually not, especially if we have large number of variables. Let me put it mathematically for you first. What I am saying is, the null hypothesis is that all of them are 0. I want to prove that this is not the case. I want to say that at least one of the betas is definitely non-zero. That is, the predictors that I have selected have some relationship with the response. So now suppose if my model is saying that any one of the predictors, say here we got 6, Suppose it was giving that only one of them, say room num, is significantly related with house price basis the p value and the rest are not. Now, can I say with confidence that since beta of room num is significantly related, I am confident that the predictors in this model are impacting the response variable? The answer is no, I cannot say that. Let me show you how. So suppose I toss a coin 5 times and I say that if I get 5 heads in a row, I will term that coin as a biased coin. Now, if this is my criteria of saying that the coin is biased, what is the probability that I will classify a fair coin as a biased coin? As you can see, probability of head in one toss of a coin is half. So what is the probability that in all the 5 tosses I'll get all the heads? So half into half into half into half into half 5 times. So it is half raised to power 5 which comes out to be 0.03125. This means that there is nearly 3% chance that I will wrongly classify a fair coin as a biased coin. Now, if I toss 100 fair coins 5 times, what is the probability of at least one of them getting all 5 heads? So these are 100 fair coins. The probability of getting a head is 0.5 again. What is the probability that at least one of them is wrongly classified as a biased coin? So this we can calculate using this formula that I've shown here. It is first finding out the probability of getting all heads in none of the case, and we are finding 1 minus that probability, and that is coming out to be 95%. You do not need to know how this came out, but the result is important. The point that I'm trying to make is, although the probability of calling a fair coin as a bad coin was only 3%, but if you are doing this experiment 100 times, it is almost certain that you will wrongly classify at least one of the coins. By almost certain, I mean there is more than 95% probability. So now this is similar to the t statistic in the sense I said that we are 95% sure that beta j is not 0 when I saw its t value and p value. So we are nearly 5% unsure. So there is a 5% chance of a beta which is 0 being classified as a non-zero beta. Now if we have a large number of variables, all having 5% chance of getting wrongly guessed as significant, it is almost certain that at least one of them is actually wrongly saying that beta for that variable is non-zero. So if we depend on individual p-values, there is a very high chance that we will incorrectly conclude that there is a relationship between predictor variables and the response variable. The solution to this problem is to adjust for the number of predictors and then find the p-value. This new statistic which adjusts for the number of predictors is called F statistic. This includes the number of variables in the form of this p. So all softwares, when we run a multiple regression model, give a F statistic value for the model and a corresponding p value. So this p value must be checked against the threshold that whether there is a relationship between model predictors and the response. If there is, then we will look at the t value and p value of each individual variable to identify which of the variables is significantly related. I hope you understand the concept. I'll briefly summarize it. The idea is, instead of looking at individual variables and saying that the model predictors are significantly impacting the response variable, we will look at a different statistic which takes into account the number of variables that we have. This ensures that we do not make the mistake of saying that the models have a significant relationship with predictor if we got that one or two of the predictor variables were significantly impacting the response by chance. So to avoid that chance, we are using this new statistic which is called F statistic. We look at its value and we look at the corresponding p-value. If this p-value is lower than the threshold value, say 1% or 5% again, we say that the model predictors are significantly impacting the response. After that, we will look at the individual predictors and their estimates and p-values. Also note, like I have told you earlier also, even if you do not understand the whole concept behind this F statistic, the concept that you should take away from this video lesson is just that you have to check whether your p-value of F statistic is lower than a threshold of 5%. You do not need to understand whole of the concept behind the F statistic. This will ensure that the model predictors that you used are having some significant impact on the response variable. In this video, we will discuss the results we received for the categorical variables. If you remember, there were two categorical variables in our dataset. One was airport with values yes and no, which we converted into corresponding dummy variable called airport yes with values 1 and 0. Second categorical variable was water body, which had 4 categories, and we made 3 dummy variables with values 0 and 1 to correspond to this variable. Let us see what our model has to say about these variables. Let us talk about the airport variable first. If we look at the equation, here I have kept only airport in the linear equation. You can keep all other variables also. So basically the equation is y is equal to all the other variables multiplied with their coefficients plus constant plus beta of airport into the airport variable. What this means is there are two possibilities. If there is an airport, which means the value of xi is 1, then we will have value of all the other predictors multiplied by the coefficients plus the constant plus beta 1. Else, if it is 0, this beta 1 will not be present since xi is 0, so beta 1 into xi is 0. Therefore, this beta of airport is straight away giving us the difference in house price if there is an airport and if there is not. So if I look at the result of my model, airport yes variable has an estimate of 1.13. This is the beta value. So this means that if there is an airport and all the other variables are same, the value of the house, the price of the house will increase by 1.13 units. Also look at the p-value for this. The p-value is low, which means there is a statistical evidence of a difference in the house price depending on whether there is an airport or whether there is not an airport. Also note that this coding of airport yes as 1 and airport no as 0 is arbitrary. We can use other values also. The result will have the same interpretation regardless these values. In the other variable, which is water body, we had 3 dummy variables. So we received 3 different beta values for all these 3 variables. So if you remember, in this we selected the baseline of water body none. That is, we said that all of these values as 0 will mean that there is neither a lake nor a river in the area. So now what is the meaning of each of these variable? Water body lake means that compared to the situation where there is no water body, if there is a lake in that area, how much will the price increase? So 0.26 units will be the increase in price of house if there is a lake in the area. If you look at the lake and river coefficient, it is minus 0.68, which means that if there is both lake and river, the house price will go down in comparison to if there was no water body in the area. And the third variable, which is water body river, it is saying that if there is a river, the house price will go down in comparison to if there is no water body in that area. Next thing we have to look is the p-value. All of these p-values are large, which means that there is no statistical evidence that there will be an impact of these three variables on the house price. So although the relationship is given by these betas, but statistically we are not confident that the relationship given by these betas actually holds or not. So this is how qualitative variables are handled and interpreted in linear model. We first transform them into dummy variables of n-1 categories. Then we run the regression. Then looking at the betas and the p-values, we interpret the result. In this video, we are going to run multiple linear regression. That is, we are going to use all the variables of our data set to predict the house price. This is exactly similar to the way we did simple linear regression. Only difference is that in the input x range, instead of just putting room num variable, we'll be putting all the variables. So we will again go to the data analysis button. We will select regression. In the input y range, we have the price column. In the input x range, we will put all the other variables. All the other options will remain the same. We have labels, we want the output in a new worksheet, and we will click on OK. So here is the result of multiple linear regression. The R-squared value for our model is coming out to be 0.72, where the adjusted R-square is 0.71. This is a pretty good value, and it means that nearly 72% of the variation in the values of house price are accounted for by this model. In the table below, we have all the betas for all the independent variables. So the first column contains the name of all the independent variables plus the intercept. The second column is of the coefficients. The third column is giving us standard error corresponding to those coefficients. Fourth column contains t statistic value. Fifth column is the p-value. We will be using the p-value to determine which of the variables is significantly impacting the dependent variable. So a value of less than 0.05 will be used as a threshold to identify the variables which are significantly impacting our dependent variable. So if you look at the values of P for air quality and for room num and for other such variables, you can see these are very small values. It is written in scientific format, that is in the exponential format. So this value is actually 8.24 multiplied by 10 raised to power minus 0.5. So this is a very small number. So wherever the number is smaller than 0.05, that is, we are more than 95% confident that that particular variable is impacting our dependent variable, we will use only those variables and we will correspondingly see their coefficients. When we are looking at their coefficients, we have to look at two things. First is the sign of that coefficient and second is the magnitude of that coefficient. If the sign is positive, that means increasing that particular variable will increase the house price. For example, in room num, I am getting plus 4.01. This means that if I increase room num by 1 unit, keeping other things constant, house price will increase by 4 units. Whereas for average distance, the coefficient is negative, it is minus 1.2, which means that if I increase average distance from the employment hubs by 1 unit, the price of house will decrease by 1.2 units. So it is important to look at the sign which will tell you whether increasing the variable increases the response variable or decreasing the variable increases the response variable. And the second thing is magnitude, that is how big is that particular coefficient. If it is 4, that means increasing it by 1 unit increases response variable by 4 units, and if it is 0.005, it means increasing age by 1 unit will have negligible impact on the response variable. So we will look at two things of all those variables which are significantly impacting the house price variable. One is sign and the other is magnitude. So in this way, whenever you have your marketing problem, collect the data for that problem. You can run a linear regression analysis just the way we have demonstrated till now, and using this final table you can identify which all variable is important by looking at the p-value and what is the impact of that particular variable using the coefficient value. Once you have this column, you can create the relationship between these dependent and independent variables, and you can predict the value of price using these coefficients. So let us see how to predict the value of house price using the coefficients that we have predicted. Let us bring one observation for which we are going to predict the house price. So for this last observation, we will predict the house price. So I am going to paste it here in a transpose way. So I had the data horizontally, I pasted it as transpose, that is why now I have this data vertically. Now as per the equation, the predicted price is going to be intercept plus the value of this crime rate coefficient multiplied by the value of crime rate plus value of resid area coefficient multiplied by the value of resid area, and so on. So in this column I am going to get the product of coefficient and the value. I will drag it down to the last cell. So this cell is giving us the impact of those variables for these particular values. Now if I add all these cells, I'll get the estimated price of house. So my model is predicting a value of 24 units for the house. The actual price for the house was 19 units. Similarly, we can predict the price of any other house for which we have the value of all these variables and we want to predict the house price. So this is how, using the coefficients, we multiply the coefficients with the value of a particular observation and add them up to get the final predicted price. In the lectures till now, we have learned how to run the regression tool in the data analysis add-in to find out the relationship between dependent and independent variables. But the regression tool of Excel has a major limitation. It can handle only up to 16 independent variables. Suppose you have a categorical variable with 10 categories, that would mean that you need to create 9 dummy variables. In such a scenario, for our problem statement, the count of independent variables would be more than 16. Therefore, we will not be able to use Excel regression tool. So in the coming videos, we will see how to use Excel solver to build forecasting models, because Excel solver can handle up to 200 changing cells. Excel solver is another tool which can be used to optimize functions. The trick here is to apply solver to minimize the sum of squared errors, which is exactly equivalent to running a regression. So if you remember from the theory lectures of linear regression, we use ordinary least squared method, which is minimizing the sum of squares. We can apply the same concept while using solver to minimize the sum of squares and get the optimum solution. Another advantage of solver is that using solver we can incorporate effects of special events. Special events are events which lead to unusual change in the sales or marketing activity. For example, in the holiday seasons, you will see there is unusual increase in sales of flight tickets or hotel bookings. On match nights, you will see there is unusual demand for pizzas, fast food, and other food delivery orders. To incorporate the effect of such special events, we need to create additional variables which will also be used to optimize the solution. Those additional variables can be handled using Excel solver. The next video is a brief introduction about solver, and you can see how solver can be used to solve problems. It is not related to marketing analytics. It is a general video to help you understand how solver helps in optimizing the solution. But in the video next to that, we'll be solving the same regression problem of house pricing using Excel solver. In this video, we will see how to use solver to solve a linear regression problem. This is the same problem that we solved using linear regression tool of the data solver add-in. But now we will manually create all the coefficients, use the solver to optimize the value of coefficients so that we get minimum squared error. This process is going to be a little lengthy than the regression method, but this will give us flexibility so that we can incorporate the effect of special events, seasonality, trends, etc. later on. So to use solver, we first need to create this additional table of coefficients. These are the coefficients which will be multiplied with the value of that particular variable in the observations to get the forecasted value of house price. So in this first observation, the forecasted value is going to be beta 0 plus beta 1 times the value of crime rate plus beta 2 times the value of resid area, and so on. So it's a sum product of these two values in the coefficients table and the observations table. Once we have the forecasted value, we will find the difference of this forecasted value against the actual price. In this column, we will square the difference to remove the effect of plus and minus signs. We will add all the squared differences and minimize them to get the optimum solution. Ideally, the solution that we get using this method should be exactly same to the regression solution that we got earlier. So let us first put the value of forecasted price by using the formula is equal to beta 0 value plus sum product this first array comma the second array. Since we'll be extending this formula to other cells, we need to put dollar symbols appropriately. So if I extend this without putting dollar symbol, the D3 will be changed to D4. But since my coefficients are only in the third row, I want that 3 to remain constant. So I am putting a dollar symbol in front of it to fix the value of 3 whenever I am dragging the cell. So this formula is ready. You can just copy paste it in your sheet also. So using these dummy values of beta, that is 111, I use these dummy values just to initialize the values of beta. The actual values of beta will be calculated by our solver. So these are only initialization values. Using these values, I am getting a forecasted value of 181. In the next cell, I'll find out the difference between this forecasted value and the actual price. So this is equal to forecast minus the actual price. This is the difference. In the next cell, I'm going to square it. This is the squared difference now. To fill all the cells below these three cells, I'm just going to double click on this bottom right corner, and you can see that all the other cells now have the same formula to calculate the respective column value. In this U2 cell, I'm going to get the value of sum of all the squared errors. So this is the sum of squared errors that I am getting with those beta values. Now I'm going to use solver to minimize the value of this sum of squared cell by changing the values of these beta cells. So I'll go to data and get this solver add-in. If you are not able to see this solver add-in option, you will have to go again to the file menu, click on options. Here you go to add-ins, click on go against Excel add-ins and tick this solver add-in option. If it is ticked, you will see this solver option here. Click on it. The first is the objective cell. We want to minimize this cell, so it is U2. It is to be minimized, not maximized. We want the error to be minimized by changing the beta cells, which is from C3 to R3. There is no other constraint on the variable cells. We are going to use GRG non-linear solving method for this problem, since the relationship between variable cells and the objective cell is kind of non-linear. We have applied multiple functions such as squares, etc. So that is why it is non-linear. Therefore, we are going to use GRG non-linear solving method. Before we click on solve, make sure you untick this checkbox, make unconstrained variables non-negative, since our beta values can be positive or negative both. So untick this checkbox and click on solve. So we have received our solution. We'll click on OK. You can see that the sum of squares we are getting is 11,886.9, which is exactly same as the residual sum of squares that we got when we ran multiple regression using the regression tool. You might not get the same solution in the first try. Whatever solution you get, just run the GRG nonlinear solver again on it till you get the same value of sum of squares. You can compare the values of betas also. The beta 0, that is the intercept value that I am getting, is minus 6.49, and in the multiple regression model I was getting the same beta value. So basically all the beta values will be similar to the multiple regression model that we created earlier. It is just another method of running the regression analysis using solver. The concept behind is same. We calculate the squared difference, we add them together, and we minimize them using the solver. The benefit of doing this is now we can add additional variables for special events and add their impact to get the final predicted price. This will include the impact of special events and help us get better forecast for whatever variable we are trying to predict. So here is the data of our retail store. So for each day of the year, I have segregated the month, the day of that month, correspondingly the day of the week, and the number of customers visiting my retail store. So since the retail store is open only on weekdays, I have 5 days of the week and 12 months of the year. I want to predict the number of customers coming to my retail store given the month of the year and given the day of the week. So first we will run the solver to predict the number of customers visiting our retail store without considering the effect of special events. Later on, we will take into account special events such as whether that particular day comes before or after a holiday, or whether that particular day is a pay day for government employees or pay day for non-government employees. For now, since we are not considering any special event, this is similar to a regression model. But we do not need to create dummy variables for these categorical variables. I am just going to create two lookup tables, one lookup table for the day of the week and one for the month of the year. The first column of this table corresponds to the day of the week. The second is the corresponding effect of that particular day of the week. So the concept is that while predicting the number of customers coming to our store, I am going to add two parts. One is the number of customers coming due to that particular day of the week, and secondly the number of customers coming due to that particular month of the year. So the predicted value of customers coming is going to be the sum of the value of day of the week and value of day of the month. So if I am predicting for the first working day of January, it is going to be 100 for January plus 100 for the first working day. So there will be the predicted value of customers would be 200. These hundreds are initializing values. I have just entered it. These will be changed by the solver to get the optimum solution. Once we have predicted the number of customers visiting, we'll find out the difference of the predicted value from the actual value. This difference will be in this column. In the next column, we will square these errors to remove the effect of negative values. Then in this cell above, we will add all the squared errors to get the sum of squared error value. This is the cell which we will be minimizing by changing the day of the week impact and month of the year impact. I hope the concept is clear. Let us start writing the formulas. The predicted value for this particular day is going to be a constant plus the effect of day of the week. So if the day of the week is 2 here, I want to get the corresponding value to 2. For that, I am going to use lookup function, particularly VLOOKUP. So I will write VLOOKUP, find this value which is 2 here in the day of week table and get me the value in the second column. So this will capture the impact of day of the week plus, now to capture the impact of month of year, I'll write VLOOKUP month value to be seen from the table and the column value to be returned is 2. Since we will be dragging down this formula cell to other cells in the column, we need to put dollar symbols at the appropriate locations. So we will fix the cells which we have in the jth and kth column. The shortcut for putting dollar symbol is F4 key. Now that the formula is ready, we'll press enter. So the predicted value is coming out to be 100 of the constant plus 100 for the effect of day of week plus 100 for effect of day of month. Now the difference is this predicted value minus the actual value, and the squared value is square of this difference. Now we will drag down these two cells to get it for all the other cells. Sum of square is going to be sum of all the values in this column. And now the model is ready. We just need to run the solver. We'll go to data menu and we'll click on solver. The objective cell is this H2 cell. We want to minimize it by changing these colored cells. No, you can notice that for separating the two series, I used a comma. We will uncheck this checkbox because the variable cells can have negative values also. We are going to use GRG nonlinear. In the options, we can increase the maximum time to 3600. We can have the derivatives to central. Click on OK and click on solve. So here's the solution from solver. We are getting these values for the effect of day of the week, which is suggesting that for Mondays and Fridays we get exceptional footfall due to the day of the week. In the months, you can see that in the middle months such as May, June, July, we get exceptionally high footfall due to that particular season, and in the months of January, February and September we get very low footfall due to that particular month. We are getting a constant value of 672, which is also very large. The corresponding R-square, which will tell us the goodness of fit of this model, can be calculated by using the RSQ function. The first parameter is going to be the array of actual values of customers coming, and the second is going to be the predicted values of customers coming. So the R-square is coming out to be 0.59. So approximately 60% of the variation in the number of customers coming to our store is explained by this simple model. Now let us incorporate the effect of special events. Special events such as whether that particular day is a salary day for government employees, is a salary day for non-government employees, whether it is a day before a holiday or it is a day after a holiday. So in this data set, I have added 4 additional columns to show the presence of these special events corresponding to a particular observation. So in this first observation, this day is a government employee's payday also. It's a non-government employee's payday and it's a day after a holiday. This second day is none of the above. Third day is also nothing. Fourth day is again some government employees payday. Such special events are to be added as per the business scenario. So So you have to look at the business knowledge and then create these special events. Now since we have 4 new variables, we'll need to create 4 more cells below this month table which will contain the impact of these 4 new variables. So beta gov, beta non-gov, beta BH, beta AH are actually the coefficients or the impact of these special events on the total sales. Again, we have initialized these 4 new variables, the impact of these 4 new variables with a value of 100. Now we have to do the same thing again. Only thing is, we'll add the impact of these 4 additional variables while predicting the value. So if the value of gov is 1, I will add the beta gov value. If the value of non-gov is 1, I'll add beta non-gov, and so on. So if I simply multiply these two, it is like this conditional statement only. So if in this prediction formula I add the product of beta gov with the gov variable value, if it is 1, it will be added. If it is 0, this product will be 0, so it will not be added. So we will simply add the product of gov and beta gov plus non-gov into beta of non-gov plus BH into beta of BH, and so on. So we'll create this new formula. We'll write is equal to constant plus VLOOKUP day of the week corresponding value from the day of the week table, comma 2. This is the same as earlier. Similarly for month, month of the year table, comma 2 plus this into plus non-gov into beta of non-gov plus BH into beta of BH plus AH into beta of AH. For the values in column N and O, we will fix them with a dollar symbol so that when we drag this to other cells, these reference values are not changed. So here is the predicted value. It is coming from constant plus effective day of week, which is 100, plus effective day of year, which is also 100, plus 300s for the government, non-government and after holiday value. So that is why it is coming out to be 600. I have double clicked on the bottom right corner to extend it to other cells of this column. Now in this cell, I'll find out the difference between predicted and actual value. In this cell, I will square it and we will select these two, double click on bottom right corner. So we have the squared errors in this last column. Here I'll add all these squared errors to get sum of squared. So our model is again ready. We just need to use solver to minimize this SSE value by changing these colored cells. Objective cell is L2. We want to minimize it by changing those colored cells. We will untick this checkbox since our variables can have negative values also. We are going to use GRG nonlinear and we can click on solve. So here's the solution from our solver. You can see the sum of squared errors is now coming out to nearly 6 million, which was earlier nearly 12 million. So we have reduced the sum of squared errors by nearly half. So for the first observation, if you compare the predicted values, the actual value was 1825. Previously, when we did not incorporate the special events, we predicted a value of 785. But when we incorporate the effect of these special events, we are so close, we are predicting 1765. This is because we are getting these positive values for the beta of these special events, which we are adding to the normally predicted value without special events, which is why we are getting a much better prediction value. These values, so this 395 for beta gov is suggesting that there is a positive impact of government payday on the number of customers visiting our outlet. So if that particular day is a government payday, it is expected that we will get nearly 400 more customers than if it was not a payday. Similar is the impact of non-government payday. Before holiday, we get 200 additional customers. After holiday, we get 252 additional customers. Let us calculate R-squared value again to compare it with the previous scenario. We'll first take the actual values and the second parameter is the predicted values. The R-squared this time is coming out to be 77%. Earlier it was nearly 60%. You can see by adding the effect of special scenarios, that is special events, we have created a model which is predicting better. It is explaining the variation in number of customers better. Now this sheet which is ready with you, it can be used to identify those particular days where your prediction and actual customers difference is very large. So if this difference is very large, we can say that that particular day is not getting predicted correctly by our model. For all those days, using business knowledge, we can identify if there is any particular trend or a pattern, such as whether on a match night we get additional customers or not, whether on the first day of the month we get additional customers or not, and so on. So we can identify particular patterns or trends when we are off, when our prediction is not very close to the actual value. Once we have identified those special events also, those can also be incorporated by adding another variable here and running the solver again. So first we can add special events using business knowledge. Once we have created this table, we can identify special events using the difference column. If the difference is very large, try to find the pattern where this difference is coming out to be large. Identify the special event which is creating this large difference and add its impact by creating another variable. Once you do all this, you can achieve very high levels of R-square and very good forecasting accuracy. Also, I hope that you can see that we have created a forecasting model. That is, if you have the value of month of year, you add its impact from this table. If you have the value of day of the week, you add its impact from this table, you add the constant from here and add the impact of special events from here to get the forecasted value. So for the next year or for any particular day, if you want to find out the forecast value, you just change the values in this particular row and you will get the predicted value here. This cell is actually giving us the predictions whenever we have a particular value, a particular set of values in these observations. I hope you understand the concept that we wanted to teach you in this section. Earlier we had learned that using regression tool of the data analysis add-in, you can run linear regression model to find out the impact of independent variables on dependent variable. But it has a limitation of 16 independent variables. Moreover, when we have so many categories, for example, here we had 12 categories in the month, or we can have many special events, it will be very difficult to handle those in linear regression. For that, we moved on to solver. In solver, we created separate cells to capture the impact of each of the variable. We changed the values in those cells to predict the value of the dependent variable. We found out the error in prediction and we minimized the total error to find out the optimum values of these independent variables. In this way, by using solver of Microsoft Excel, we are incorporating the effect of special events in forecasting. And we recommend that whenever you have large number of variables, you should use Excel solver instead of regression tool. When we are trying to forecast sales of companies' products, it is important to understand the concept of trends and seasonality. Seasonality is that characteristic which is time dependent, that is, when the data experiences regular and predictable change which recurs every calendar year or is particularly dependent on a season or a particular month of a year. For example, ice cream sales increase in the season of summers and decrease in the season of winters. So if you look at this graph, seasonality is the recurrence of this inverted V shape which is recurring every year. So every year at some point of time the sales increases to a particular point and then it suddenly decreases to another point. Trend on the other hand is a pattern of gradual change. So in general, if your company is growing, that is, if the product sales are increasing overall over a period of time, that is over 5 years, 10 years, that gradual change in the product sales is captured by the trend. Trend is not impacted by the seasonal effects within an year. It is a gradual change over the years. So if you look at this graph, the trend would be a curve which is increasing from nearly 100 and going up to nearly 600. So this upward curve will be a trend, and within this curve these inverted V's is giving us the seasonality. When we are forecasting sales, we need to segregate the impact of seasonality and trend when we are forecasting the future sales. So this is the problem statement that we'll be solving in the next video. We have monthly airline miles traveled by our customers between certain time range. We want to identify what is the effect of seasonality, that is, some time of the year would be holiday season, some time would be less preferred by the travelers. So what is the impact of different seasons of the year on airline miles traveled, and what is the in general trend, that whether airline miles traveled is in general increasing or decreasing. Secondly, we also want to forecast what will be the future sales in the coming months for our airline company. So before we jump into our software tool to predict the sales, There are two models which we can use to predict the sales. The first model is called additive model. In the additive model, when we are predicting sales for a month, we take into account three features. One is the initial value of sales without any trend, without any seasonality effect. In that initial value, which is considered as the base value, we first add the impact of trends, which is how is the monthly sales increasing for our airlines business. So that per month increase is multiplied by the number of month for which we are calculating it. The last is incorporating the effect of season, that is seasonality for that particular month. Using these three features and adding them together, we can predict the sales for future months. So for example, in the first month, suppose we had 100 units of revenue. After 12 months, if we are getting a revenue of 220 units per month, the base will be considered as the revenue in the first month. So that is 100 units. The trend is 220 minus 100. So 120 over a period of 12 months, that is 10 per month. So that 10 per month multiplied by the period number. So if you are predicting sales for 5th month, it will be 10 into 5. Plus we have to incorporate the effect of seasons. So for the particular month of May, if we had higher sales, we'll have to add some value to it. If we had lower sales, we'll have to subtract some value from it. That will be the seasonal index for that particular month. This is the additive model in which we add the three features. Then there is a multiplicative model. In this model, we multiply the three features. The definition of base remains the same. It is the initial value of sales or revenue, whichever we are forecasting, at the beginning without any seasonality. But the trend now represents the percentage monthly increase in the level of airline miles or whatever parameter we are calculating. It is the monthly increase in that. Seasonal index is now giving us the percentage by which our variable is above or below the average month. So earlier it was absolute increase, now it is percentage increase. That is why we are multiplying it with the base value. So we have two models, one is additive model, one is multiplicative model. We'll be using solver to identify the three features: base, trend and seasonality. Once we have identified these three features, we'll be using it to forecast future sales or future revenue. So here is the air miles data corresponding to the month and years. So I have data of 34 months with me, which starts from July 2015 to April 2018. Corresponding to this month, I have taken out the month number using the month function of Excel. So for the month of July, I am getting a month value of 7. For August, I am getting it as 8. The first column is containing the month number to represent the time interval. I told you in the theory lecture that we take a initial value, which is the base value, after which we add the monthly increase with the time interval or the time month number value. So that first column is giving us the month number, that is for the 10th observation, this is the 10th month. Similarly for 11th, 12th and so on. So the first column will be used to calculate the trend effect. The third column, which contains the month number, it will be used to calculate the seasonal effect of that particular month. This fourth column contains the actual air miles traveled in that particular month. And next we will be calculating the forecasted value of airline miles. In the next column, we'll find out the difference between forecasted values and the actual values, which will be our error. In the next column, we will square that error to remove the effect of negative errors values. Then in this particular cell, I will take the sum of squares. This is the cell I want to minimize. On the right, I have two small tables. These are the variables which we will be changing to get the forecasted values. The first value is the base value. Second is trend. Trend will be multiplied with the month number column. So if I am predicting the value for 5th month, I'll use the base value, base plus month num is 5 multiplied by the trend value, plus I will include the effect of seasonality. Since the 5th month number is corresponding to the month of November, which is 11, I'll take out the seasonality effect from this cell corresponding to 11. I'll add all these three to get the forecasted value. The last cell in the seasonality table is average. This is the average of seasonality effect of all these 12 months. The average of these 12 months should equal to 0. Since seasonality is not an overall gradual increase or decrease, it is the impact in that particular month. Overall, it has no effect at all. To signify that overall the effect of the 12 months is negligible, I am putting the average to 0. So I hope you get the point. The point is seasonality captures only the individual month's impact. So all the months cannot have positive impact. Seasonality itself means that some months have positive impact and some have negative impact. So if your sales increase exceptionally in the months of summer, they will decrease in the months of winter. So overall, we want the impact of seasonality to come to 0 for the whole year. The gradual increase from year to year should be captured in the trend part. I hope the concept is clear. Now let us put the formulas in the sheet. Forecasted value is going to be base plus trend value multiplied by the corresponding month number value plus the effect of seasonality for that particular month of the year. So we will have to look up that particular value in this table. We'll use VLOOKUP function. We'll write VLOOKUP this month value 7 from the seasonality table and we want the corresponding value in the second column. We'll press enter. It is coming as date because the format is set to date. I'll change the format to general. So here is the forecasted value. I added the base value, which is 30, plus trend into month num 1 into 1, which is 1. So 30 plus 1 31, and the seasonality value, which is right now set to 0. All these values 30, 1 and zeros are initializing values. They will be changed by our solver to get the optimum value. I'll put dollar symbols for the jth and kth column so that when I drag this formula down, this reference cell does not change. Now I can just double click on the bottom right corner to extend it to other cells. Now error is going to be the difference between forecasted and actual values. The next column is squared of this value. We'll extend it further. This is the sum of squared errors. So sum all the values in this column. Now the model is ready. we have to minimize sum of squared value by changing these colored cells with the condition that the average seasonality impact is going to be 0. So let's open solver. The objective cell is this H2 cell. We want to minimize it by changing these colored variable cells, comma, these other cells, and with a constraint that average impact of seasonality is 0. Untick that checkbox if that is ticked for you. It should not be ticked since the value of all these variables can be negative also. We are going to use GRG nonlinear solving method. We can click on solve. We have the solution. Click on OK. You can see that we are getting a base value of 37. That is, if there was T0 a month before this initial month, in that month, without any impact of seasonality or trend, the base value was going to be 37. Then we have a trend impact of 0.05 or 0.06 nearly, which means that each month on an average 0.06 is getting added to this base value to get the total air miles traveled. This table contains the impact of seasonality. You can see in these 2 months the value is negative. You can see that in January or February the impact is negative. That is, usually travelers do not travel in January and February, whereas in the months of June, July and August it is very highly positive. That is, the air miles traveled is more in these 3 months. So if you want to forecast using this model, just add another row of observation. For example, if I am trying to forecast the sales in the month of May 2018, it is going to be the 35th month in our trend. May is 5th month of the year, so the impact of seasonality would be for the 5th month, and I just drag down that cell which is forecasting the value, and I'm getting a value of 40.71. This means that in the month of May 2018 the predicted airline miles travel value is going to be 40.71. This is how we use the additive model to predict when there is seasonality and trend in our sales or revenue. Now we are going to see the multiplicative model. In multiplicative model, instead of adding the 3 impacts, we are going to multiply the base with the trend impact and the seasonality impact. So when we are forecasting the value of airline miles traveled, we'll use the base value and we'll multiply it with the trend raised to the power the time period, because the trend is capturing the percentage increase in one time period. So if we are calculating it for the second time period, we have to multiply trend again, so that will be trend raised to power 2. If we are doing it for third time period, that will be multiplying the trend effect again, that will be trend raised to power 3. This is similar to compound interest in the sense that we have a base principal value. If you want to calculate the interest for the 5th year, you have to raise interest to the power 5 before multiplying it with the principal to calculate that particular year's interest. Once we have multiplied the base with the trend effect, we will finally multiply it with the seasonality effect. Seasonality again is also defined as the percentage change in the sales due to that particular season or that particular month. So again we are going to multiply that particular season effect. There will be one more change. In the additive model we had average here, which was sum of the seasonality effects for the 12 months. In the multiplicative model, since the seasonality is going to be multiplied with the base into trend value, we are not going to use the average of these 12 months. We are going to use the geometric mean or the product. That product should be equal to 1. That is the overall impact of multiplying seasonality with the 12 months of data should be 1. So if the concept is clear, let us start writing the formulas. First is the forecasting formula. In the forecasting formula, we will have base value multiplied with the trend value raised to the power the time period value, which is this first column. Then we multiply this with the seasonality value of that particular month, which we will get by the lookup function. So this is the forecasted value with the multiplicated model. We'll put dollar symbols at the appropriate location. You can use the shortcut of F4 for applying dollar symbol. In the next cell, we will calculate the error between forecasted and actual values. In this cell, we will have the squared values of the error. We will select these three and click on the bottom right corner. In the sum of square field, we will get sum of the squared errors. Now the model is ready. We are going to use it in the solver. So we are going to minimize this objective cell by changing those colored cells, comma, the seasonality cells, with the constraint that this cell is going to be equal to 1. We are going to use GRG nonlinear solver. The unconstrained variables can have negative values, so untick this checkbox and click on solve. So we have the solution. The base value is coming out to be 37.25. There is a trend of 1.001, which means that every month there is an increase of 0.1% in this base value, which means there is an upward trend in the airline miles. For seasonality, you can see in January and February, the multiplication factor is less than 1, which means that in January and February, airline miles traveled is less than other months of the year. Whereas for the months of June, July and August, it is more than 1, which means that in this particular season, the number of customers traveling is higher than the average. If we compare the solution of additive model and multiplicative model, the sum of squares was coming out to be 5.6 nearly for the multiplicative model, whereas it is coming as 4.9 for the additive model. This is suggesting that additive model has lesser error while calculating for this particular scenario. So these are the two models, additive and multiplicative models, to incorporate the effect of trend and seasonality while forecasting future sales or future revenue or any other variable that you want to forecast. So we have seen how to forecast values of a variable using the additive and multiplicative model. There is another method which is called moving average method, which can be used to forecast values of variable when we have seasonality and trend. In this method, we follow 4 steps. The first step is to deseasonalize the level of series during each period. This means that we remove the effect of seasonality from the data. Then we use this data to fit a trend line. We use this trend line to predict or forecast the future values. Then we determine the seasonal index of each quarter or each time period and use that seasonal index on the predicted values to calculate the values which have both trend and seasonality. So the process is remove seasonality, predict future values, estimate seasonality effect, and then re-seasonalize the predicted values. So by following these 4 steps, we will forecast the future values when we have trend and seasonality. In the next video, we will see an example in which we have data of product sales for 20 quarters and we want to predict the values for the next future quarters. So here is the data for which we are going to forecast the values of sales for the next 3-4 quarters. So in the first column, I have the quarter number. It starts from 1 and it goes up to 20 for which we have the data. Correspondingly, we have calculated the year and quarter. So for quarter number 1, year is 1, quarter is also 1. Quarter number 2, year is 1, quarter is second. Similarly, if you look at quarter number 10, year is 3 and quarter is 2. And corresponding to each quarter number, I have the sales value. Now the first step is to remove the effect of seasonality, that is de-seasonalizing the data. To remove the effect of seasonality, we will use the concept of moving average. We will find out the average of 4 quarters to remove the effect of seasonality in each quarter. Since when I take 4 quarters, it completes 1 year within which we are considering the seasonality effects. So I will be taking moving average of 4 quarters within 1 year. When I am considering 4 quarters, that will cover the complete year, thus remove the seasonal effect of individual quarters. So when I take average of first 4 quarters, it comes at a middle value of 2.5. Since I do not have this 2.5 midpoint, I will note down this value at the second quarter. Then I will again calculate average for next 4 quarters. The average of this is coming as 3.5. So I will put this value at the third quarter. When I take the average of this 2.5 located value and 3.5 located value, I'll get the value for the quarter 3. This is the centered moving average for quarter 3. So I hope you get the concept. We first calculate the moving average for first 4 quarters that we put in the cell corresponding to quarter 2. Then we calculate for next 4 quarters that we put corresponding to quarter 3. We calculate the average of these two values and we put it in front of quarter 3 as the centered moving average for quarter 3. These values in this column, the centered moving averages, the seasonality effect has been removed from these values. So we can consider these sales values, that is the centered moving averages, as values without any seasonality effect, and we can straight away extend them to calculate the future forecast. The forecasted values from these values will also not have seasonality effects. We'll have to add the seasonality effects later on. So till 4 period MA and centered MA, we would have calculated the effect of trend. This column centered MA will give us the effect of trend, and using that trend effect, we will be forecasting the values in these cells below. Later on, we will use these two columns to include the impact of seasonality and then calculate the final forecast values in these colored cells. So if you are ready, let us start writing the formulas. So this cell is going to have the average of first 4 quarters. The next cell is going to have the average of next 4 quarters. We can drag this down for all the other cells. So we will get this till the 18th observation only, because when we reach this 18th quarter, we are already using up the 19th and 20th quarter values. Below this, we do not have any value, therefore we cannot go any further. Now, in this cell for third quarter, we are going to take the average for second and third cells. So this again goes up till the quarter 18. And now we have these values for which we have only the effect of trend on sales and the effect of seasonality has been removed. Now we can use these values as the y values and the quarter number as the x values to fit a simple regression line. You can do this in the same way we have done earlier, that is, you can use these values, plot a scatter plot and plot a trend line, get its equation. You can do it using the regression tool of data solver also. Here I'll show you another method. In this method we will straight away calculate the slope and intercept using the slope and intercept formulas of Excel. You must be knowing that slope is the coefficient of x, that is it is beta 1, and intercept is the constant, that is it is beta 0. So you can straight away calculate the slope and intercept in Excel when you are doing simple linear regression using slope and intercept formulas. So we will write those formulas is equal to slope. First value is going to be the value of y, which is centered MAA, and the x value is going to be the value of quarters. This is giving me a slope of 6.93. This slope is suggesting that in each quarter there is an increasing trend, that is we will sell on an average 7 more units with each quarter. Now let us calculate the intercept. For that we will use the intercept function. Again we will use G7 to G23, B8 to B23 and enter. So the intercept is coming to be 30.166. So now we have the slope and intercept. You know the equation that we have created, y is equal to slope times x plus intercept. Here if I put that equation, I can predict the values using this trend. So it is slope times the quarter number plus intercept. We'll need to put dollar symbol for the slope and intercept value. You can see we have predicted these four values 175, 182, 189 and 196. These predicted values do not have the effect of seasonality in them. Now we have to re-seasonalize these values to get the right forecast. To get the effect of seasonality, we will use the ratio of actual sales values and the centered moving average sales values. So the ratio of actual versus CMA is 61/55 for this case. And if I drag it down, I am getting this ratio. So this ratio means that without the seasonal effect, sales was 55 But when we include the seasonality effect, we have to multiply it 55 with 1.1 for the third quarter to get a value of 61. This means that in quarter third, seasonality increases the sales by 10%. If you see the effect of seasonality in quarter third of next year, I am getting a value of 1.13. That is, it is having a positive effect of 13%. Since I have 4 values of this ratio for quarter 3, I'll take the average of this ratio for each quarter to say that this is the effect of seasonality for that particular quarter. So in this cell, I'll take the average if the quarter value is 1. So I'll use the function average if. The first is the range, which is quarter range D8 to D23, comma, we have to check it with this value of quarter table, and if it is this value, we have to average from this ratio column. We'll put dollar symbols at the appropriate locations and we'll press enter. So the seasonal effect for quarter 1 is coming out to be 0.81. I'll extend this to other quarters to get the seasonal effect of each quarter. Now since we are multiplying this seasonality index for all the 4 quarters, the seasonality index product should come out to 1, since overall there should be no impact of seasonality in the total sale of the year. The overall increase or decrease in the sale of the year should be covered by the trend line only. So now our aim is to get seasonality indexes whose product is going to will be equal to 1. To do that, we are going to first find out the product now. So currently the product of these 4 seasonal indexes is coming out to be 0.98. Now we need to find a number using which, if we divide all these seasonal indexes, the final seasonal indexes that we get should have a product of 1. To find that number, we will use the power function. In the power function, we'll find the nth root of this product number. The n will be the number of categories that our data has. So here we have 4 quarters, so we'll use n as 4. If we have 12 months for which we are calculating seasonal indexes, we'll use n as 12. So we'll find out 1 by nth power of this product. So we'll write power this number to the power 1 by 4, which is 0.25. So this is the number with which, if I divide all these seasonal indexes, I'll get the normalized values. So let us put this divided by this special number. We'll put dollar symbols and we'll drag it down. So now we have normalized seasonal indexes. You can find the product of these 4 to just check that now it is coming out to be 1 or not. You can see now the product is 1. So to normalize the values of seasonal indexes, we first find out the product, then we raise that product value to 1 by nth power, where n is the number of categories. If you have quarters, it will be 4. If you have months, it will be 12. The mathematics behind this concept is beyond the scope of this course. However, you just need to know how to do this. You do not need to do the maths behind it to use it. So we'll use these normalized seasonal indexes. We'll multiply the predicted values in these cells with the corresponding seasonal index of that particular quarter to get the final predictions. So in this we will write is equal to this value multiplied by the seasonal index of this quarter. That can be found out using the lookup function on the quarter table. So we will write VLOOKUP this value comma the quarter table comma 3, since we have normalized indexes in the third column. We'll put dollar symbols on the table values and we'll press enter. This 144 is the predicted value when we have incorporated trend and seasonality both. So moving average is another method. We have seen additive and multiplicative models. Using moving average, we have segregated the effect of trend and seasonality and implemented them separately to forecast the future sales.